Hello. Hi, good morning, and welcome to AMCAP 6. I am Musharraf, and I will be your host for these 2 days, and we are going to get started very soon. I just need to make some announcement. First, I want to get a show of hands of like whether any of you have downloaded the content of the exercises that we sent out yesterday. Thank you so much. And another thing is we have the Wi-Fi open, is International House. I guess some of you have connected already. Try not to put too much pressure on it because we share it with the actual International House, with the people who live here, and we don't want to bring it down. And one of the things I was told that people, even though they are here, people for some reason wants to look at the online streaming that is going on YouTube. Please try not to do that and look at the podium. You will see what's going on here. And with that, I am glad to introduce Jan Stryker, who is the co-director of the MLlab, and we're going to hear where we stand after 5 years. Thank you.
Thank you, Musharraf. Very happy to see you all here. Thanks for coming. I hope that you are going to really enjoy the 1.5 days of the 6th AMCamp. So let me dive in. So I'm going to present you about what happened during the last year with Berkeley Data Analytics Stack, or like we say to call it BDAS. So this is the 6th AMCamp, and we came a long way. I remember it's actually, I was checking this, and the first AMCamp 1 was just 3 years ago. It seems an eternity. But this is how things appear in retrospect. On many events happen between a particular time in the past and the present. And there are a lot of things happening indeed. In terms of training, I was looking at aggregating the numbers. It's again, the numbers, precise numbers are hard to get. We trained through AMCamps like here, through SparkR summits, and we have also MOOCs I'm going to talk a little bit about, tens of thousands of people, certainly over 20,000. And today we are here at the AMCamp 6. We have over 210 people registered, and again, thanks for being here. So AMCamp, it's hosted and by the MLlab, as you well know. And MLlab was this project started at Berkeley in 2011. It was a 6-year project, so we still have 1 year. And it was a fantastic partnership between the public and private sector. We got funded by NSF, DARPA, and Department of Energy. From the public sector, government, and on the private sector, we are very happy to have worked and still working with some of the greatest companies. Amazon, Google, IBM, and SAP have been the founding sponsors, and then we had, I think, over other 30 sponsors during this time since we started the MLlab in 2011. And one of the main goals of the MLlab was to build this next generation of the open source analytic software to be used across academia and industry, and this is BDAS. So what is BDAS? Going in more detail, it's like I mentioned, it's an analytic stack, big data processing stack, and basically it consists of 3 layers, like many other analytic stacks. It's a storage layer, it's a resource management layer, and processing layer. As a storage layer, and this stack doesn't exist in isolation. It's actually interoperate very well with the other big data stacks in the industry, in particular with the Hadoop stack. So actually, as a storage layer, we leverage the existing storages out there, like HDFS, S3, and so forth. And on top of that, we provide some layers which gives you extra functionality, like Succinct, which you are going to hear today. It's one of the newest projects in the MLab, which allow you to query on compressed data. Tachyon, it's a project we started 2 years ago, and you are also going to hear about it. Actually, it's quite a mature project and a successful project at this time. It started to provide you an in-memory storage layer. And then at the next layer, the resource management layer, we have Mesos, and Mesos was actually the first large project we started in the context of the BDAS stack. This is where everything started from. Mesos is from everything started. And we also interoperate, like I said, with the existing stacks, and in particular at this layer with Hadoop Yarn, the resource manager. So you can use either of them with the components, the rest of components we developed. And finally, the processing layer is where the bulk of our effort went. And here there is a bunch of systems. The most important one has been Spark, which is a parallel execution engine. You'll hear more about that. And on top of it, there are a lot of other components, libraries to provide support for different workloads from streaming, machine learning, SQL, and so forth. And finally, we also started this project 1.5 years ago, Velox, which is a serving layer, right? So you have your recommendation engine, you produce the results, so you want to serve this recommendation to the end users, okay? So today and tomorrow, you are going to hear only about a subset of these components. It's impossible in 1.5 days to go over all of them. And in particular, you are going to hear about the status and what's new in Spark. And Spark is, again, it's a substack in this stack, right? Everything there, it's in blue. It's what Spark is today. It's a SparkR, which is an execution engine, and these libraries on top of it, like I mentioned, to provide support for different workloads. And you are also going to hear about these other projects like Succinct, Tachyon, Velox, and Keystone ML, okay? So next, I'm going to focus, like I mentioned, it's what happens over the last year or so. And one thing and one theme it's emerging is that the industry impact is accelerating. Today, there are thousands of companies using various components of the BDAS, and there are actually 3 well-funded startups behind the BDAS main components, the most mature components so far. Mesosphere behind Mesos, Databricks behind Spark, and Tachyon Nexus behind Tachyon. So next, let me talk a little about the largest component, Spark, and then at the end, I'm going also to touch on these other components you are going to hear over the next day and a half. So Spark. It's a parallel execution engine which unifies a variety of workloads, batch, interactive, streaming computation, and it provides a powerful, flexible API which makes it much easier to write big data applications, and it's also fast. It provides bindings in various languages, Scala, Java, Python, and most recently we added support for R, data scientist. And this is, it got a lot of traction, in particular in the last year. So let me give you some numbers and to show you some nice pictures. So this was a meetup, the meetup groups around the world in January 2015, okay? It's open source. The meetups are places or people congregate to exchange the latest news, to hear the latest developments, and to socialize, right? And this is October, last month, 2015. You can see visually it's a lot of more red points in a lot of more places. If you look at the numbers, the number of meetup members, actually since January this year until October, so 10 months, increased from 12,000 to 42,000, 3.5 times. So we are on the track to quadruple the number of meetup members this year alone. And you can look at other numbers. This is the numbers of Spark Summit attendees. Last year, we had one Spark Summit in San Francisco, 1,100 people. This year, we had 3, New York, San Francisco, and Europe. It's again, the total number of attendees increased 3.5 times. And if you look at a little bit older numbers, if you look at the developers, also increased from last year, it's contributing to the Spark, increased 2 times. Okay, so that was on, it's meetup members, core Spark members, and so forth. What about the new people, coming to Spark? So, very excited to say that what we've done here is that for next year, we had 2 massive online courses. And these are developed by people at MLlib, which are hosted at Databricks for the year. And these courses are extremely successful. The first one was Introduction to Big Data with Apache Spark, and it was developed by Anthony Josephs. Many of you know him. So again, he took a year off and spent with Databricks people and developed these courses. And then it offers this course through edX, and we had close to 80,000 people. It was a 5-week course, pretty heavy. Some people spend hundreds of hours, to take this course. And the completion rate was 12%. Maybe for some of you, this seems low, but for people who knows about the completion rate for the MOOCs, is twice as high as the average for the edX. And edX is one of the best, highest quality platform for MOOCs, if not the highest. Typically, the completion rate is between 4 and 6%. The second course was taught by Amit Tabalkar. This again, many of you know him. He was here, he was a postdoc with the MLlib for the last 3-4 years. Then now is a faculty at UCLA. And again, he took 1 year off during which he developed this course, which is scalable machine learning with Apache Spark. And 55,000 people, more than 55,000 people, completion rate 15%. So very excited, there will be more MOOCs in the future for the next year. So I encourage you to take some of them. At the same time, we've seen larger and more meaningful deployments using the BDAS stack, and Spark in particular. So the largest cluster to date, we are aware, it's over 8,000 nodes. It's Tencent in China. It's the largest single job, more than 1 petabyte of data processed. In terms of streaming, we have the largest streaming intake, 1 terabyte per hour. And also, we are, we own the on-disk sort record for the last year. The results for this year will be published soon. In terms of ecosystem, I'm happy to say that today, a large number of big data vendors, Hadoop distributors, including their distribution Spark. Everyone, Cloudera, Hortonworks, MapR, IBM, now SAP, and so forth, and many others. We also are seeing a lot of more and more applications being built on top of Spark or being integrated with Spark. BI tools predictive systems, and many more. So next I'm going to give you even more numbers, but these are from a survey. So it says for Spark Summit in San Francisco this year, we conducted a survey, and we had over 2,000 attending conference, and 1,500 responded to this survey from 840 companies. So it's a broad spectrum. And there are three strands we notice. We are seeing more and more diverse applications. We are seeing Spark being run in more and more environments over more and more storage, different storage systems. And we are seeing more types of users, okay? So what you'd expect from a growing platform. So what are the top applications? Well, the top, it's a business intelligence, right? So you interface the BI tools with Spark for analyzing and exploring big data using existing BI tools, something like Tableau or some Click or some new ones like Zoom data and so forth. The second, you may not be surprised, data warehouses. People are dealing with more and more data sources, structure and structures. They need to fuse them, and they need to then they need to process them, and they need to query them to explore the data. So this is what Spark is one of the sweet spot of its use. Then recommendation, machine learning. Spark is one of the first target application for Spark was machine learning, so no surprise here. Log processing and user log processing. Its logs are often unstructured. Spark is great for processing unstructured data. And user-facing services, when you do predictive systems, recommendation systems, and things like that, they have a user-facing component, of course. And we are seeing more and more applications also in the financial sector and insurance. Right? It's fraud detection and security. What about, again, Spark? It's in itself a stack. So what about different components and their popularity? It's, again, you may not be surprised here, but the Spark SQL, it's the most used out there. And why? Because there are many, many people knowing SQL, right? Data frames, I'm going to touch on that, and you are going to hear from Josh a little bit in the next talk. It's a new abstraction, which is data scientists and data analysts are very familiar with it from Python, Panda, and R. We just released it this year, very successful. Spark streaming, okay? So it's again, very successful. And machine learning and GraphX, okay? So for all these cases, almost 60% or more, they are using these components. And it's more surprising, like Spark, one of its strengths is the fact that provides you support, unified support for multiple workloads. And we are very happy to see that the user take advantage of that. As you can see, 75% of the users use more than one component. Like I mentioned, so Spark, it's just to be very clear, it's a processing engine, okay? And now the question is, where is the data? Where does the data sit? And of course, one of the traditional storages for big data technologies, HDFS, right? And the Hadoop stack, which is the most popular, still probably the most popular big data stack, is having this storage, and then it's coupled with this execution engine, which is a MapReduce, right? So this is what you have. And just to emphasize what I said earlier, in the case of Spark, it is decoupled. Spark is an execution engine and can work on different storage layers. Okay, so the question is that which are the most popular storage layers Spark is working on? This was 2014. As you might expect, a lot of usage was on top of HDFS. This year, we see a much higher variety. It's HDFS, NoSQL, like Cassandra, MongoDB, and so forth, or proprietary SQL, like Oracle, SAP, and things like that. And you see there, not a big difference. It's still Hadoop, HDFS, it's a little bit in front, 46%, but NoSQL is 43%, so it's almost a tie there. And proprietary SQL, 37%. So actually, if you look the other way, if you know SQL and proprietary SQL, you exceed the use cases for use instances for Hadoop. Now, Spark, it's also working in on top of different environments, runtime environments, and it can work standalone, or it can work, if you have your Hadoop clusters, you can deploy Spark on top of Yarn or on top of Mesos, which was the first resource manager we supported. This again, here you see a lot of usage in standalone. So the significant here is that this is not used together with a Hadoop system. And Yarn is still a big chunk with 40%. Another interesting data is that 51% of the people who answer the survey, they do have at least a pilot in the public cloud. And that number is increasing rapidly, but based on all this most recent article, you shouldn't be surprised about this trend. Okay? The other question, and one of the last, is that what about the users, the type of users who use Spark? It's again, Spark provides bindings for different languages. Here what was data for 2014, Scala, most people, Spark is natively written, it's written in Scala. So Scala, it's a native API. So no surprise here, most of the users use Scala. And then quite a few used Java and Python. This year, Scala and Java decreased. Scala is still the most popular, but look at Python. Python now is the second most popular, 58%. And R, it wasn't supported last year. Now it's supported. You already see 18% of people using R. And what about the fastest growing user segments, right? It's like can you guess which is one of them? Windows users, right? So we have more and more Windows users, almost 3 times increase. So I guess this is a sign of becoming, it's well accepted by the large number of developers. Streaming, it's increased by 56%. This also it's basically what we see more and more companies. You do analysis, you get the data you get the results on historical data, and then you want to do it to get these results faster and faster. And of course, when you go on this spectrum, at the end of the spectrum is streaming, right? Get the results in real time as soon as you get the data. And this, again, shouldn't be a surprise. Spark SQL, very popular. This big increase is the fact that Spark SQL was just released less than 2 years ago. Okay? So what next? Where we are going from here, right? It's a very successful platform used by many people. Very vibrant, and like I mentioned, the growing is actually accelerating. However, we are doing a lot of things, and I have to say that one thing, and Josh will make that point next talk, is that during the past year, actually past 9 months, we are seeing some of the biggest changes and improvement in Spark since Spark has been created in 2009. And two of them are, as I mentioned earlier, the use of data frames. So raising the level of abstraction, data frames, think about like tables, but these are a lot of libraries for data scientists, and this is a primary abstraction in R, and also very popular in Python with pandas. And we are basically at the point rewriting all the libraries and on their data frame instead of resilient distributed data sets. If you remember, that was the old abstraction. And what these data frames give you also, it gives you the schema. So give Spark more information so Spark can do better optimizations. That's one of the keys. It's one of the things you have the cake that is much easier to use for use, you know, and you can eat it too because you have more knowledge, you can optimize more. And data sets, think about data frames with types, is type data sets. So we are going there. And performance, on the performance side, you know, Spark was fast, was faster than MLbase, much faster. That was not as hard. But you know, now as the API matures, it's a more and more drive to make it, to increase the performance. And this project Tungsten, it's exactly that, trying to bring Spark performance closer to the bare metal. Okay? And one of the things Tungsten it's using again, these data frames. The fact that you know the schema of the data allows you to keep the data in the binary representation. And this has huge benefits. For instance, you get rid of deserialization, which is very expensive to bring the data from the storage to memory. It gets rid of the memory overhead because the deserialized data is much more expensive in terms of memory, in terms of storage than serialized one. It's in, you know, when you load a pretty, a reasonable complex data structure from the disk in memory, the memory usage increases 6 to 8 times versus disk. And also, as anyone who knows, who used Spark knows, you know, it's garbage collection is a big problem. When it hits you, right? So also alleviates that problem because now you are not going to have a lot of small objects. You are going to have big blobs where you keep this data. And we are doing a lot of efforts with integrating in the existing ecosystems, more and more supporting more and more storages, and supporting more and more workloads. Okay? I'll have another 4 minutes. Okay, so this was about Spark, and then I'm going to go quickly through the other components you are going to hear about. Tachyon. Okay? So Tachyon is a non-persistent storage engine. Initially it was in memory storage engine, now supports also its own SSDs and other storage devices. Supports think about it's a layer which sits between the application and the persistent storage layers. So supports more and more APIs for the applications and supports more and more file systems and storage systems underneath. And the cool thing actually about why you care about the Tachyon, you know, despite the fact that you can keep data in memory, so it's fast not only for Spark but for other cluster computing systems, is that traditionally it's very hard to innovate as a storage layer. Because you don't want to change the storage layer because if you introduce bugs, you lose the data, right? So it's very hard to evolve those. So what Tachyon allows you by introducing this layer, you can innovate at that layer because that's non-persistent, right? While you keep the persistent layer, you know, as it is, so to speak, right? So it provides this layer, or you can innovate in the storage space, okay? Succinct, it's one of the newer projects, and it's very cool. It allows you to query on compressed data. Think about you can do substring matches on the data, arbitrary substring matches, searches, while the data is compressed, gzip level of compression. And there are numerous applications. We have regex support. You are going to hear about that. Graph query engines. You can have graph queries on top of this compressed representation and many more. Keystone ML, it's a next generation of pipelines. When you really write this machine learning application like prediction systems, there are many stages, right? Getting the data, featureization, applying machine learning prediction algorithms and models, creating the models and things like that. So this Keystone ML, it's a superior way which allows you to build these machine learning pipelines. It has already a pre-built set of operators, pretty rich, and it has type-safe interfaces, right, between these different components. You can glue them together. Velox, it's basically our serving layer is to close a loop. Once with Spark, you can create these sophisticated models, these predictions, fraud detection systems. But then you want also, you have a user-facing, right? When you go to Netflix, you want to get an answer immediately about what are the recommended movies for you. So this is what Velox is. It's providing this service layer. And it's not only that, it provides you online management and maintenance of these models, and it does support a variety of predictive models. So with that, just to summarize what today and tomorrow you are going to hear and have hands-on exercises on some of the latest and greatest component of BDAS, including new features in Spark, Tachyon, and Succinct and Keystone ML. And you are going also to hear about some applications and tools which are developed for BDAS. It's ADAM, which is a framework for very fast genomics analysis, quite successful. You are going to hear about Planck, which is a tool which tells you, try to predict if you have an application, a job, what is optimal number of nodes and the type of nodes you want to run the job to minimize the completion time or minimize the cost if you do it in Amazon. And Slash, which is easy to use API for stochastic machine learning algorithms. So in summary, for many of these BDAS stack components over the past year or past few months, we are seeing a more and more accelerated adoption. For instance, for Spark, almost on all dimensions, we see year-over-year increase of 2 to 4 times. We are seeing more and more large scales production deployments, and more major enterprises making use of the BDAS stack technologies. And the impact in one word was well beyond our expectations. And believe me, we had high expectations when we started. But for this, really, I like you to, thanks to everyone also here, we are nothing without users. We are nothing without contributors, and of course, without our sponsors. So thank you, and hope you are going to enjoy a great event.
Thanks, Jan. Next, we have Josh Rosen, who is going to talk about what's happened in Spark 1.5, what's happening, and what's going to happen soon. Thank you. Let me just set up your machine for you.
All right, great. Can everybody hear me? Cool, great. Thanks. My name's Josh Rosen, and today I'm going to be giving a deep dive into the features in Spark 1.5 and a look beyond into some of the upcoming work that we have for 1.6 and future releases. I've been a longtime contributor to the Spark project. I began my work with the project when I was a grad student in the AMP lab at UC Berkeley. I'm currently working for Databricks as a software engineer, where I work on SparkR, SQL, PySpark, and many other components of the stack. Here's a photo of me actually introducing PySpark in AmpCamp 1, just to kind of give a sense of how long I've been working on this stuff. So my employer, Databricks, was a startup that was founded by many of the Spark creators from the AMP lab. We offer a hosted service for running Spark on EC2 that has interactive notebooks in your web browser, dynamic plot visualizations, easy cluster management, and scheduled jobs. And we have a 14-day free trial if you want to check this out. Just because I know there may be a lot of academics in the audience, I want to also mention we have an academic access program that you can check out for instructors or research. In this talk, I'm going to begin by giving a brief introduction to Spark SQL and the new data frames API. I'll then give an overview of Project Tungsten, this performance optimization effort that Jan alluded to. Most of this is landed in Spark 1.5, but this work continues into Spark 1.6 and future releases. I'll give a brief tour of some of the other new features that we have in 1.5 and a preview ahead at what you can expect in Spark 1.6, which should probably be out by the end of the year. So Spark SQL, which is most of what I'll talk about today, is part of the core Spark distribution since Spark 1.0. And sort of no matter how you measure it, it's one of the most active components of the project, either by number of commits or number of distinct contributors. Spark SQL allows you to run standard SQL queries or HiveQL queries on top of Spark. And you can run this alongside an existing Hive deployment or to replace one. So it has lots of interoperability with tools that people are already using. What's great about this is you can actually connect many tools that speak SQL to your Spark cluster using Spark SQL. For instance, you can connect Tableau or other sort of business intelligence tools and use Spark to run those over massive data sets. Spark SQL has native bindings in all of the languages that we have Spark for, including Python, Scala, Java, and R. But a key point that I want to emphasize is that even though SQL is in the name, Spark SQL itself is not just about standard query language queries. In Spark 1.3, we introduced a new API called data frames. And a data frame is a distributed collection of rows which have associated schema with them. And it provides an abstraction to users for doing filtering, selection, aggregation, and plotting. And this is very familiar to users of data frame APIs in Pandas or R. But the main distinction here is that these data frames run in a distributed fashion and are subject to SQL query optimization, which I'll go into in a little bit. For people who have used earlier versions of Spark, you'll recognize this as a successor to an earlier experimental API that we called SchemaRDD. And data frames have a lot of nice advantages. A major advantage of them is letting you write less code. So here we have some code written on the RDD API for computing an average. So here our data is in a tab-separated text file, and we split each line into a key-value pair, and for each key, we compute the average. And you have this kind of big, messy Lambda functions. This sort of workload is very easily expressible in SQL if your data has already been given a schema. Like I just say select name, average age from people, and it's very natural. Using the data frames API, we have a very similar programmatic API for doing the same thing. Here I can basically create a data frame from a SQL table that's named people and do that grouping and aggregation. It's a very natural API. And again, this API looks very similar across all of the languages that we support. In addition to writing you less code for doing your actual data transformation, Spark SQL makes it very easy to interoperate with data sources that have a notion of schema. Spark has many built-in data sources for reading common formats like JSON, Parquet, ORC, various forms of text files. But we also have a stable extension point so you can plug in a third-party data source that can take advantage of many of the optimization opportunities that the built-in ones have. So there's many of these available for connecting for things like Avro, Redshift, various CSV formats, and stuff like that. there's actually an index of these at sparkpackages.org that has a big directory of sort of third-party integrations for connecting to different data sources. And to provide an example of just sort of how much boilerplate that this API can save you, here's an example of loading data and data frames using these data sources APIs. So here I have a bunch of data that came from a text file, which contains some JSON data, and I want to read that in and do something with it, and then save it back out to Parquet. And you can see in the slide here, I have dataframe.SQL context.read and dataframe.write to sort of enter the reader-writer interface. I can specify different configuration options to say how the data should be loaded. For instance, for JSON, how much of the data should I sample to automatically infer the schema and types? Or in the case of Parquet, I can say, how should I handle partitioning? How should I handle the presence of existing data when saving? And then to finish things off, you actually just specify where to save it. So this is a very convenient API. So in addition to letting you write a lot less code, data frames have major performance improvements too. As you'll see from this graph, which is just taking a look at the time to aggregate 10 million integers, a fairly simple query, you'll see that for the data frame APIs across all of the supported languages, we have about the same runtime, which beats that of the RDD API. And to sort of give it a little bit of intuition for what's going on here and why we have these sort of fast and stable across language performance results, I want to point out how Spark SQL actually executes queries. In Spark SQL, whether your query is specified using SQL syntax or as a data frame, these get compiled into a logical plan that understands the data types and the operations involved in your query. And this plan goes through multiple phases of optimization, like it would in a traditional database, where we take that logical plan, do various logical optimizations, physical planning optimizations, until at the very end, we compile it down to an RDD execution plan that Spark actually runs. And this common execution pipeline and intermediate representation shared across all languages means that these performance improvements apply to all of those APIs. So speaking of performance, I want to kind of move on now to take a look at Project Tungsten, this major performance optimization effort that started in Spark 1.4 and has spanned all those subsequent releases. The goal of Project Tungsten is to prepare Spark for the next 5 years of software and hardware trends. If you kind of look at the hardware landscape over the last few years, you'll see that we've had orders of magnitude increase in storage system performance, in network performance and bandwidth. We see solid-state disks being deployed, 10 gigabit Ethernet is increasingly common. But one area that we've seen proportionately less improvement is in raw CPU processing time. And as a result, there's a lot of workloads for which CPU efficiency has become a bottleneck instead of the more traditional I/O costs that we're used to dealing with. And the goal of Project Tungsten is to attack these bottlenecks head-on via optimizations in Spark. The main sort of pillar of this optimization is manual memory management and data structure layout, which I'll talk a little bit about in the next few slides. We also make heavy advantage of runtime code generation to remove many JVM bottlenecks and get very efficient code, sort of rivaling what you might write by hand. Finally, there's many optimizations throughout the individual query operators, aggregation, sorting, hashing, things like that, which combine to add up to very, very big end-to-end improvements. And just to run through that, in Tungsten, we're taking a look at all of the building blocks of query processing in sort of a bottom-up fashion, all the way from data representations to network layers to the actual join operators themselves, and looking at them from a performance perspective. And I want to just pause to note that many of the optimizations that we're doing are deeply steeped in traditional database systems research and principles. So a lot of these ideas are not fundamentally new. So just to dive right into this first point, data representations, the sort of foundation for understanding the rest of what we've done. I want to talk a little bit about how Java objects are used in Spark and what this sort of means from a memory and performance standpoint of view. So traditional Java objects have two key downsides, space overheads and garbage collection. In terms of space overheads, if you take a look, in many cases, at the size of the actual data itself, say you're dealing with some strings, you have some UTF-8 bytes, you're dealing with sort of a compound record of a bunch of columns, you have just the data for those columns, you'll find that if you represent this naively as Java objects, it ends up taking significantly more space. In some cases, hundreds of % overhead and waste. And the reasons for this sort of are many-fold, but it can actually add up, and I'll show you a little bit more on the next slide. In addition, in many big data applications, if you have literally tens or hundreds of millions of Java objects in your heap, this wreaks havoc on Java's garbage collection heuristics. And this may manifest itself as very, very long GC passes, out of memory errors. It's sort of a big problem. So in Tungsten, we sidestep both of these issues by sort of stepping aside from the memory safety of the Java object model and choosing to actually lay out data by hand in large regions of managed memory. So much like you would in C or Java, we're doing sort of struct packing, laying out the memory ourselves. And that extra control unlocks a lot of other optimizations, and it gives us these space and GC improvements. Sort of to look at this more concretely and look at sort of space overheads, let's consider a simple row object, a building block of row-oriented query processing. So here I have a row with 3 columns, 1 integer and 2 strings, and my example row is 1, 2, 3 data bricks. And if we were to represent this sort of naively as a Java object graph, it's probably at least 5 objects. We'd have an array with 1 slot for each column, and inside of that array, we have 1 object for each value, and those have their own object overheads. So, you wind up with a graph or a single row of very, very many objects. You have lots of space overheads because each of them has a high overhead. And another somewhat more subtle problem, if you want to compare 2 of these rows for exact equality, if you want to hash them as a building block of another algorithm, you now have to sort of walk this multi-object graph, and it's an expensive process. So let's consider a more efficient representation of this very same data and take a look at how in Tungsten we choose to encode this. So in Tungsten, we actually have a manual row layout that looks something like this. Our row is divided into 3 different segments. We have a region of bits at the front, a bit set for tracking whether fields are null or not. For numeric columns, basically any numeric type from a long, a short, an end to double, we have a fixed length section where for each value we store 8 bytes and we just store their small values right there. For longer values, whose length could be arbitrarily big, like a string, what we do is we store a pointer in that fixed length section to some variable length data that we append to the end of the row. And the nice thing about this is all of the data for the row is laid out contiguously in memory. So if we want to hash 2 rows, we're just hashing sort of opaque bytes. It's very fast. If we want to compare 2 rows for equality, we're just doing 2 linear scans through memory. It's pretty efficient. And to look at this concretely, here's that same example row, 1, 2, 3 data bricks, encoded into our unsafe row format. And here we have a null tracking bitmap at the beginning, and because all of the columns are present, it's just empty. The 1, 2, 3 value, because it's a small number, is just stored immediately inline. And for our 2 string columns, we store relative offsets in that fixed length data section to the string data, which is stored at the end in a variable length section. So this is an example of sort of a flat one-dimensional data structure, how we can encode that. And sort of moving up the level of abstraction stack, we can look at more complicated data structures like a hash map. And we'll see that we get big benefits there too. So again, drawing a comparison with just using Java objects, we can take a look at the standard Java hash map, which consists roughly of an array where you actually do your hashing and probing. And for each entry in the array, we have sort of a linked list of entries for each key value pair in our map. And the problems of this, again, similar to the row, we have huge object overheads because every entry is at least 3 or 4 objects, right? You have an entry for the hash map.entry itself, the key, the value, that's kind of bad. In addition, sort of a problem that strikes sort of more here is memory locality. The actual data that's stored in your hash map might be sort of scattered all over the Java heap. It's not sort of dense in memory, and that has sort of bad performance problems sometimes. Another sort of subtle problem that can occur here is size estimation. Frequently, we want to actually know the exact amount of memory being consumed by our data structures so that we can gracefully respond to low memory conditions. For instance, if we don't know how big a hash map is, it's very difficult to actually gracefully spill data to disk when we're running low on memory. And to sort of work around this, Tungsten and in SparkSQL, we have our own map that we call bytes to bytes map. And the way that this works is roughly we still have our array, except we've stored data a little bit more densely. We store the hash code there so we don't have to recompute it. And when it comes to storing the actual data in the map itself, we just lay it out, because this map is append only, in just a big contiguous region of memory. So there's you don't pay an object overhead for each entry. And the other nice, beautiful advantage of this is that if you want, at the end of an operation, want to scan through every key value pair in the hash map, which is actually a fairly common operation, it is just a linear scan through memory. You're not having to chase pointers and sort of go all over the heap. So this gives you huge cache efficiency, processor efficiency benefits. Sort of moving on to look at another class of optimization that we've done in Tungsten, I want to look at code generation. So expression evaluation is a major part of query processing. For instance, if I have a numeric expression like a plus a plus a, during query parsing time, this ends up becoming sort of an object graph that corresponds to that expression. And the naive way of evaluating this would actually be to call functions into that object graph to compute your arithmetic. And of course, this is going to be extremely slow, right? Because for each value, you have all of these virtual function calls, you have all of these very hard to predict branches, you're creating and boxing objects all over the place. It's fairly inefficient. Now, if you were to write this by hand, of course, you just write a plus a plus a, and it would compile down to efficient Java bytecode, and that would be that. So in SparkSQL, what we've gone ahead and done is implemented runtime code generation, where we will actually generate efficient code that rivals the performance of what you would get by hand, but happens automatically in a matter of milliseconds during query processing. Now, this code generation has existed in earlier versions of Spark 2, but we've actually dramatically improved it in Spark 1.5. When it comes time to do the actual code generation, we've swapped out the compiler engine used to compile that code that's given order of magnitude speedups, which can make a difference for very low latency queries. In addition, beginning in Spark 1.5, we have a giant library of built-in functions. And for all of these, we have very efficient code-generated implementations. And what's great about these is you can actually use these in place of like a user-defined function in your data frames code and see huge performance benefits because we can run the super optimized code-generated version. So for instance, in this example that I have here, both in Python and Scala, we have some dates and we're filtering them based on this function. Yesterday is the day before the current date, and current date is a built-in function. And this actually gets compiled down into an efficient sort of logical plan, which gets emitted into very, very efficient code, no objects being created. It's great. So sort of moving a little bit up the abstraction stack to look at other optimizations that we've done. Aggregation is a major building block of a lot of analytics queries, and we've done many optimizations there in 1.5. Probably some of the biggest changes are that we've done a major refactoring of the internal aggregate interfaces, which allows us to use new operator implementations that more gracefully respond to memory pressure. So in the next slide, I'll show you an example of a new aggregation operator that's based on our tungsten hash map that I showed you. And what's great about this is that when we run out of memory, it'll gracefully spill data to disk instead of ooming. So to look at what this actually looks like, here we have a diagram of the life cycle of incoming records to our aggregation operator. So like the previous operator, when a record comes in, we probe it against an in-memory hash map to see if there's a match. If there is, this hash map where we're storing the running totals of our aggregation, we do an in-place update. And what's cool about this, recall that in that hash map, all the data is serialized just raw bytes in that tungsten format. And when it comes time to actually update our aggregates, we don't allocate any objects, we don't swap any rows, we just reach right into that region memory, overwrite those integers or those running totals. So it's very efficient, no objects being created. Now, if our size estimation, our very accurate size estimation, because we know how big everything is, because we laid it all out by hand, if that estimation says that we're running low on memory, we'll actually take the data that's in memory, sort it by key, spill it to disk, and start over and keep going. And over time, we will have accumulated a lot of these sorted, partially aggregated runs on disk. And once we've seen all of our input, then we'll take these sorted things and very efficiently merge them together and take those partial aggregates and do the final aggregation at that point. And this basically lets us scale up to arbitrarily large numbers of keys in any task without running out of memory. And just one point I want to underscore here, which is that, of course, if all of the data happens to still fit in memory and we didn't need to spill, we won't spill preemptively. So I mentioned sorting in that slide. We've also optimized the process of sorting, an operator in its own right, and also a building block in terms of aggregation. So one of the major changes that we've done to sorting is something called a prefix sort. And the kind of provided some intuition for what that looks like. If you consider a naive basic sorting algorithm, it looks something like this. You have an array which stores pointers to the objects that you're sorting. And your sorting algorithm operates, in some sense usually, by looking at pairs of items and saying, what is their relative ordering? And usually the way that this works is you grab both items, you go and you look at the actual items themselves, and you directly compare those two items for ordering. Now the problem is those two items can be located in just completely random regions of memory, and that comparison, chasing those pointers, comparing those records, kind of expensive. And the thing is, in many applications, you don't have to look at the whole record to determine relative ordering. If I have two rows, Alice and Bob, I only have to look at the first character of each of their names to determine the relative ordering. So a prefix sort intuitively is a way of taking advantage of that optimization to do fewer full comparisons. So in our array, where we're storing pointers to what we're sorting, we actually store a bit of additional information, part of the key, or a subset of the columns that are being sorted on. And if we can, we do comparisons on those first. If that comparison says this record is definitely before that one, we don't actually bother to dereference the pointers and actually compare those full records. And the nice thing about this is it gives you very big cache efficiency improvements. You're not searching over memory in a random fashion. Now, of course, so we've gone ahead and done this in SparkSQL in our new sorting implementation. And of course, we've optimized other parts too. The actual comparison of two records itself goes through that aforementioned code generation, so that's much faster. We've optimized a lot of compression and serialization things too, so we can sort directly on compressed data. So using this, we actually built an external sort that, similarly to the aggregation pipeline, gracefully deals with running out of memory. And again, it's a very similar idea. We operate in memory as long as we're able to, sort of doing an in-memory sort. If memory pressure is low, sort what we have, spill it to disk, and then merge it together at the end. And I want to share with you just some sort of performance numbers. The axis labels here are a little bit weird because these are some customer data sets, so I can't share the exact size. But on the left-hand side here, we have a relatively small data set. We have scale factor, like number of keys being aggregated on the x-axis, and runtime on the y-axis. And Spark 1.4 is in orange, 1.5 here is in blue, and lower is better on these graphs. And as you'll see here, our new aggregation and sorting operator gave us performance benefits even for the relatively small data set. So we weren't actually spilling or running out of memory at this point. If we scale up to a much, much, much larger data set, which we have on the right-hand graph, you'll see here that we actually see sort of nice, graceful scalability properties as we grow our data set, roughly linearly. And Spark 1.4, on the other hand, looks like it got exponentially slower, like it was running out of memory, and then I think it couldn't complete the query at some of the larger data set sizes. So this actually winds up being a big resiliency benefit for users doing huge data sets without having to tune anything. Now, of course, finally, we've also done optimizations to joins. Again, an important building block of query processing. We have a new sort merge join, which uses sorting instead of hashing to be able to scale up to large out-of-core data sets. And at the planner level, we actually prefer to use that now as opposed to other sorting algorithms when we can. Another area that we've optimized is something called a broadcast join, which, if you're not familiar, is an optimization for the fairly common case where you're joining a massive data set against a very, very tiny one. For instance, you have a giant fact table with millions of customer rows, and you're taking a very, very small zip code lookup table and joining that. In this case, it makes a lot more sense to broadcast the smaller of the two tables and avoid shuffling the very, very big one. So we had broadcast joins before. Now we plan them for a significantly greater variety of queries. And again, just to underscore those scalability benefits, here's an example showing for Spark 1.4 and Spark 1.5 the advantage of planning a sort merge join as opposed to a hash join for a query, just looking at scalability here. Finally, just to kind of underscore a few of the benefits of Tungsten operating on serialized data, because we can operate on data in a serialized form, end to end, even across process boundaries when we're shuffling data over the network or when we're broadcasting, we avoid the cost of a lot of data serialization and deserialization things. If we want to shuffle data, since it's already just bytes, we just shove them right over the network and there's no new format change that needs to happen. And that's a big efficiency improvement. And similarly, if we're doing broadcasting that small table for broadcast join, the Tungsten format benefits us there. Now, just sort of moving to some user-facing improvements that actually allow you to see a little bit of this query planning in action, I want to kind of point out one of my personal favorite features in Spark 1.5, which is this new visualization of query execution concepts for Spark SQL. So if you go to the Spark driver web UI today on Spark 1.5 and you are running a Spark SQL context, you'll see that there's a new tab up there called SQL. And for every SQL query, whether it's executed through the data frame API or through Spark or the SQL interface, you'll get this nice plan diagram that shows you the physical query plan that was generated by Spark SQL. And maybe it's a little bit difficult to see on the slide here. I guess you can't really see it. But inside some of these boxes, there's actually statistics that it prints on the number of rows processed by each operator. So for a filter node, for instance, you can actually see how selective is my filter, how many rows is it cutting out. It's very easy to actually see that overlaid on the actual plan because we do that nice statistics collection now. Now, of course, there's a lot of other visualization improvements in 1.5, and if you want to know more about these, there's a talk from my colleague, Andrew Orr, that he gave at Spark Summit Amsterdam that goes into a lot more detail on this. Now, there's a lot of other improvements in Spark 1.5 that I haven't even scratched the surface on, and I think that you'll hear more about them in the talks this afternoon on streaming and MLlib. But I just want to acknowledge there's a lot of work there too. So just looking forward a little bit, I want to kind of provide a preview of some of the stuff that we have in the works for Spark 1.6. And of course, again, this is a massive amount of work. These are just a few personal highlights I want to kind of point out. So a big new feature that we have experimental for Spark SQL is what we're calling adaptive query execution. And this aims to sort of address a common problem. Imagine that you're analyzing a new data set, and it's the first time that you've ever seen this data set. You don't have any statistics at all to guide your query optimization. You don't know the number of keys, the number of columns, number of rows, nothing. In this scenario, this is sort of hard for traditional cost-based statistics-driven query planners, but we still want to do something, right? So what we've done is we actually have it so that Spark, at runtime, midway through the query, can execute part of the query plan, gather some statistics while it's running, and then at that point actually decide degrees of parallelism, operator selection for latter parts of the query plan based on those sort of just-in-time statistics. So this is sort of an exciting feature of relieving the user of the need to pick the degree of parallelism, and they can kind of still get good out-of-the-box performance. This was sort of, for those familiar, an offshoot of the Shark work that was done in the AMP lab at Berkeley. Another major change that I've done a lot of work on is something that we're calling unified memory management. Again, the aim here being to remove a lot of configuration and tuning and get better out-of-the-box performance for average users. So to provide some background, today in Spark, instead of an executor, you have a certain amount of memory. And Spark reserves a certain fraction of that memory for caching, and the rest for query execution. And the problem with the sort of static partitioning of your heap into here's my cache memory, here's my execution, is that if you don't end up using cache, you still pay for it. Or on the other side of the coin, if you end up caching a lot of data and needing very little query execution memory, you don't have it if you haven't configured it in advance. So in 1.5, we actually break down the static wall between these two regions, and Spark can kind of dynamically grow and shrink them in response to demand. So giving you out-of-the-box performance with no tuning. For users of Spark SQL who deploy many applications and users on the same Spark context, we have improved session management in SQL. And this means that you're actually able to have some sort of degree of isolation between users sharing the same Spark cluster, so that if both you and I wanted to find tables that have the same name in our interactive sessions, we don't have conflicts. And finally, the other big feature that we have, new user-facing API in Spark 1.6, is an experimental new API called datasets. And this is a compile-time, type-safe API on top of the Catalyst and data frame engine. And to kind of provide a little bit more detail about what this will look like, this is type-safe, like the RDD API. You operate on case classes and domain objects, and you get all of those static typing guarantees. It is fast. We actually preserve enough type information that Spark is able to automatically generate efficient encoders and serializers and deserializers for your data. We no longer have to rely on Java and Cryo. We get these big tungsten representation improvements. And it's designed to be interoperable, that you can kind of convert between the data frame and the data set APIs as you choose. And to provide just a very quick preview of what this actually looks like, let's say that I have a data frame that I've read here from JSON, people.json. The schema here will automatically be inferred from the records. I didn't have to do any explicit typing if it wasn't necessary. And let's say that instead of working with the sort of data frame row interface, I want to work with a case class called person. So here I go ahead and I define a case class, and I have my data frame, and I say just take this data frame and view it as a data set of person, and because the columns and type matches, that all works. And now I can actually operate on this data set, like I would of a case class. But what's great about this is what I write here gets compiled into a logical query plan and goes through all of that catalyst optimization that we saw earlier. So this actually looks a lot like RDDs, but it's actually able to benefit from a lot of the tungsten improvements that we've gone ahead and done. And of course, what's nice is, again, you can actually build up to much more complex examples. So if we're here, I'm computing a histogram over the values for each user, and it's a very natural API. This will be a big for like machine learning users, people doing sort of complicated pipelines or data frames and other sort of types of code. I think people will really like it. And this will be available in Spark 1.6. I think there'll be a preview of that soon-ish. So just to recap, the tungsten optimizations that I talked about today are all available in Spark 1.5. They are on by default, meaning as a user, if you're using data frames, if you are using SQL, you don't have to do anything to benefit from this out of the box. We offer large performance improvements for SQL and data frames, to a lesser degree if you've used the RDD API, but really we need the additional type informations and schema and semantics that the data frame API gives us to do these optimizations. So if you're writing new code, I encourage you to try those APIs out. And many, many improvements in the pipeline for Spark 1.6 and beyond. So that's it. Thanks, everybody.
Thank you, Josh. We have 1 or 2 minutes to take some questions if you want.
Those were relative scale factors. Yeah. Oh yeah, the question was about on those graphs, the scale on the x-axis. And I believe that those data sets are from some customer data sets, so I don't have the exact numbers, but those are relative scale sets. So as you progress in each increment, it would be like X times bigger than the previous. I think we were running on the order of like, hundreds of gigabytes on the right graph.
Thank you.
Do we have time for any more? Or?
We have time for one more question.
I'll be around afterwards too if folks want to mingle and chat. So.
I have a question specifically about the integration with the JDBC driver or SQL.
Yeah.
You mentioned that there's a lot of optimizations that are done in terms of a planner. Have you ever thought about spilling some of those optimizations down to like the actual SQL layer if you're interacting with a database?
Yeah, that's a good question. Yeah, so we actually do a number of optimizations there. For instance, if we're talking to an external JDBC data source, we will push down filters, we'll push down column pruning. There's some work looking at pushing down more complicated fragments of the query plan too. It's a little bit tricky depending on the different semantics and support of different databases, but it's something we thought about. I can chat a little bit more offline too if you want to know technical details about how these filtering and scanning optimizations work. Thanks.
Let's thank the speaker one more time. Next, we have Haoyuan Li, or also known as HY. He's going to give us update on the storage part of the BDAS stack.
Thank you, Musharraf. So good morning. I'm Haoyuan Li. People also call me HY. And today, I'm going to talk about the open source status of the Tachyon project and give you an introduction to Tachyon, basically for whoever haven't heard of it before. And it's basically what Tachyon was like before this year. And then talk about the deployments of Tachyon in production and some new features we have in Tachyon and talk about how to get involved. So here's the background. So we started Tachyon from MLlib UC Berkeley in the summer of 2012. And the project got open sourced in the following year, in April 2013. Now it's like 2.5 years ago. It's open source under Apache 2.0 license, and the latest release is version 0.8.2 in this month. And the project has been deployed at more than 100 companies. So Tachyon now is one of the fastest growing big data open source project. There are many metrics, just to illustrate just one of the metrics. So this, in terms of the contributor growth, so we had one contributor at the beginning for our version 0.1, and we had a 300% increase, and which is 3 contributors for 0.2, and then 15 contributors 30 contributors, 46, 70, and 111 for 0.7 release. And in the latest release, we have more than 170 contributors. Compared with AmpCamp last year, so we have more than 3 times increasement in terms of the number of contributors, and we have more than 50 organizations are contributing to the project as well. So I want to use this opportunity to thanks to our contributors as well as users. This is the snapshot of that link, which is our community link in our website. This graph is auto-generated from the GitHub, like a number of commits. So the more the commits you do, the more bubble you have in this graph. I want to thanks to these companies who are either using or contributing to the project as well, like Yahoo, Intel, IBM, these companies. And just one example of production deployment, Baidu is deploying Tachyon in production. They run Spark SQL on top of Tachyon. And under Tachyon, they run Baidu internal Baidu file system and use Tachyon tier storage concept feature to manage both memory and HDD. And the deployment actually nowadays is around 200 nodes, and it's managing PBs of space under Tachyon management. And it brings like 30 times performance improvement for Baidu's workload. So that's just the open source background. So then I'm going to give brief introduction to Tachyon, the status before 2012. So Tachyon is an open source, memory-centric distributed storage system. So then the people ask, why do you want to do this new storage system called Tachyon? So here's the reason. So there are 2 reasons, mainly. So one is a performance reason. For memory is fast, and DRAM throughput still increase exponentially every year. On the other side, disk throughput increase slowly. So then we have the result that memory locality is the key to achieve interactive response time. That's the performance side. And then let's look at the price trend. So memory is getting cheaper and cheaper. So the DRAM price decrease around 50% every 18 months. So as you can see from this figure, at the early 2000s, companies from Wall Street, they started to embrace memory technology aggressively. And then after that, the company like Google, like Baidu, they started to embrace that as well. And now the rest of us in the world start to embrace it like aggressively. So this trend has been realized by other people as well. Like we have Apache Spark from our lab. You have a HANA in-memory database and others as well. Then the question is the problem solved? So the answer is no. Otherwise, I wouldn't be talking here. So we're still missing a solution for the storage layer. And let's show if we have a solution in the storage layer, what new things or what type of issues we can address. It's just a small example we show like before this year. So this is one example showcased with Spark. And you know what Spark, based on George's talk, it has been widely deployed in many companies, and you know how it works. So I'm not going to spend time here. But there are still issues not covered by Spark. Say it's a computation engine. So it means that in many companies, when you have your complex data processing pipeline, you have to do the data sharing between different Spark jobs or even jobs with other frameworks as well. So in this particular case, when you do this data sharing, you have to go through an external like storage system. Say, for example, on the left side, you have a Spark job 1 write something into either HDFS or Amazon S3 if you deploy in cloud. And then on the right side, you will have another Spark job load the data back. And this data sharing process is slow. And as I mentioned, you could have your legacy code like written in MapReduce, but you still want to use it. You have a lot of investment there, even though you want to write a new code in Spark. So that's how to share this data efficiently. And the solution with Tachyon is very simple. So basically, we just run Tachyon in the middle between like computation frameworks and storage, and like traditional persistent storage, like Amazon S3, like HDFS. In this case, these frameworks just interact with Tachyon to get a very fast memory performance throughput. That's the first showcase. The second case is in Spark or in-memory computation engine, like the way they store the data now, in-memory data nowadays is to keep the data in same JVL, the same process as the compute engine. This means that if the compute engine crashes, you also lose the data in the same process storage engine, and you will either recompute the data or reload the data back from outside storage, which could be time-consuming. So that's a second showcase. So in this case, how we deal with it is still very simple. You just run Tachyon in the middle, and then you will see you keep all the data, in-memory data in Tachyon safe, even when the job crashes. And in this case, you can still, other jobs or this job, you can still load the data from Tachyon space as the memory speed. That's the second one. And the third one is, let's talk about data sharing. Data sharing for the different jobs for the processing part. So think of a very simple example. You have two Spark applications, Spark jobs, and they want to process the same input data. And the way you do it today is that you load the data, the same data, into two different Spark applications, right? So in this case, you will have an in-memory data duplication issue. That's the first one. And the second one is a garbage collection because it runs on top of the JVM. So that's the third issue. And the solution is still very simple. You just keep the in-memory data in Tachyon. And in this case, you only need to keep one single copy of the data in Tachyon, and all the different jobs, they can process and read this data from Tachyon as a memory speed. And you don't have the in-memory data duplication issue. And because you load the data from Tachyon's memory as the off-heap storage, and in this case, you have much less garbage collection issue as well. So to enable what we just mentioned, so there are two features we talked before, but I'm going to briefly mention this today. The one feature is the memory-centric architecture. The other feature is we push lineage down to the storage layer. So for the first feature, so this is the architecture of Tachyon. We have the single logical master, which keeps tracking the location of the data, as well as the status of every worker node. And then we have the workflow manager to manage lineage information. And then on top of, in every worker node, we also run a worker daemon, which manages a local space, the tier space, as well as reporting status to the master node and the response remote I/O request. And on every worker node, we also run a RAM disk, which keeps the real in-memory data. And when you have a Tachyon client, when you have the locality, it will access the RAM disk directly without going through the worker daemon to guarantee the memory performance. And of course, we have the master fault tolerance, and you can use we use a zookeeper to do leader election in this case. That's architecture. And the lineage concept in Tachyon is also very simple. So it basically describes the relationship among different files or data. So in this particular example, as you can see, you have a Spark job reads a file set A and generate a file set B. And if you have another Spark job reads file set C and generate file set D. And later on, you have a MapReduce job reads B and D and generate E. And Tachyon remember this information reliably. This means that when these jobs write data into Tachyon, this job only need to write one single copy of data into Tachyon's memory at the memory speed. And Tachyon will guarantee the fault tolerance. If in any case, like say, file set E get lost, Tachyon will be able to launch necessary recomputation to get the data back. That's the lineage concept in Tachyon. And that's a very brief introduction or summary of what happened before 2012. And then let's talk about the new deployments and new features we had during the past year. So first of all, this figure we want to show is I want to emphasize where Tachyon sits in the stack, what it really enables. So Tachyon sits in the middle of the computation engine and the persistent storage systems. This means that it enables new workloads in any storage system. I'm going to talk about some real use cases later on as well. And this means that they'll bridge new workloads as well as improve the performance to the under layer. And to the up layer, it will bridge new data as well. Say, previously, you only can access data in this particular cluster. And now you can also process the data in your remote cluster as well at a very good performance. And of course, at this new layer, we can easily innovate on the API to make data access, store, or manage much easier as well. So, and the second thing is I want to talk about the Tachyon running in the production environment, both in the cloud and on-premise as well. So this is one case. I already talked about the Baidu case, and I'm going to talk more about this anymore, but this is another use case. This is a leading oil company. They run Spark on top of Tachyon, and they run Tachyon on top of Gluster file system. And in a lot of scientific computing, they use Gluster file system. And they use Tachyon to manage memory only. And in this case, they bridge the data, bridge the new workloads between the traditional data, and they can analyze the data in the traditional storage. That's one use case. And the other use case, this is a SaaS company. And they run Impala on top of Tachyon, and they use Tachyon to load the data from S3, Amazon S3, and use Tachyon to manage both memory and SSD. And they have around 15 times performance improvement. And the next one is a biotechnology company. They run both Spark and MapReduce on top of Tachyon. They also use Gluster file system and use Tachyon to manage local memory and SSD. And is another one, it's a SaaS company. They use Spark on top of Tachyon, Tachyon on top of S3, and they use Tachyon to manage SSD only. And this is a leading retail company as well. This is a leading retail company. They use Tachyon on top. They use Spark and MapReduce on top of Tachyon, Tachyon on top of HDFS, and they use Tachyon to manage memory. And from these examples, what you can see that Tachyon runs everywhere, and it's really like run on top of any like different persistent storage, and you can run different frameworks, share the data among different frameworks through Tachyon. And as Yang mentioned in the earlier talk, like as this being this innovative layer here, and we enable like faster innovation in the storage layer. So I'm going to use some features in the following slides to showcase, to demo this. So one common question we got like before is that like people say, like even though memory performance is still going up and the price is going down, but still memory expensive. If you compare to SSD or like HDD. So then the question is, what if the data size exceeds a memory capacity? So then we introduced a tiered storage concept feature in Tachyon. Basically, you can have any number of tiers managed by Tachyon space. And as you can see, memory, SSD, HDD, or even like NVRAM or whatever like new storage media you may came out. Like the new announcement from Intel and other companies. And in this case, you can configure Tachyon to manage, like you say, I want to manage memory only. I want to manage SSD only. I want to manage like memory plus HDD. And this all depends on your own cost analysis and how important the latency or the performance is to your workloads in your production. That's the tiered storage concept. Even though we introduced this feature only this year, and now we are seeing this feature is running in different companies like production. Like I mentioned, Baidu, they are running petabyte, they are using Tachyon to manage petabyte of space, which is pretty exciting. And the other feature on top of this is, like people say, okay, you have this tier storage, so I have a lot of data. Some data I think are more important than other data, and I want to keep the most like hottest data like in your most highest performance tier. And in this case, we have different like policies you can choose to say how to do the data eviction from upper layer to lower layer, or how you can promote your data from the lower layer to the upper layer. And beyond that, which is more interesting is we realize that in many different companies, if you have the resource and if this workload is super critical to you, you may want to investigate yourself, like what's the best policy for you. So we also have the interface, and you can like implement your own like policy to do this allocation and eviction. That's the pluggable data management. And of course, like you say, you have some data super important, and you just want to pin this data in a memory space, you can have the pin operation in Tachyon, and you can unpin it later as well. So that's one important feature I just talked about, which is tier storage. And another very cool feature or very interesting feature is the transparent naming. So what does this mean? So previously, before before this feature, what happened if you deploy Tachyon is that if you write data into Tachyon, Tachyon will put the data into the under persistent storage, right? So when you do this, in the under persistent storage, your naming, the file naming, is some format only understood by Tachyon. This means that for all your application, you have to go through Tachyon at the same time. So for some company, this is doable, but for some other company, this takes a long time. So what this enable is that, so nowadays, if in this case, you say like you wanna configure the under storage is HDFS. In Tachyon space, you have data folder, you have user folder, and in the under storage, Tachyon will create the same hierarchy for the folders and the same file name as well. What this enable is that, first of all, it's much easier for users to deploy Tachyon in production, because even say Tachyon fails, like you still can access data in your way. But like even though we don't, we don't think it fails like in production. But anyway, and the other thing it really enables is that after writing the data through Tachyon, you have part of your applications talking through Tachyon interface. And your other part of applications, your legacy applications, you can still like communicate with your persistent storage like at the same time. So in your production environment. This is really powerful. You can migrate your workload step by step. And for some legacy workloads, you can just choose, say, I will never migrate those workloads. I don't care. So that's what this feature enables. So, and after this feature, what's even more interesting is that we have a new feature called unified namespace. What does this mean? So from the stack figure you see, below Tachyon, you can run all type of persistent storage. And our users say, okay, I have this I3, I have HDFS and my own cluster. I have cluster file system, this and that. And whether I want to access data, all those data at the same time, but I don't want to like manually like ETL, like transfer the data migrate data from one cluster to another, which is painful. So then with this feature, basically what we can do is you can mount and unmount a particular persistent storage under a particular Tachyon folder. And this means that your application, you only need to talk to Tachyon namespace, and Tachyon namespace and Tachyon system will help you to access data in different under storage system like transparently for you. So which is very easy to use and very easy to manage data for you. And it's also very fun as well. So, and after that, we have many more features. And due to the time limitation, I'm not going to talk about like them in detail. This is some, I'm just going to elaborate some of those. One thing is we have a remote write support. So previously, we require you have a Tachyon worker daemon running on the node, which you have a Tachyon writer. Now it's not required anymore. You can write to remote Tachyon memory. And we have easy deployment. So previously, you can only do standalone deployment. Now you can deploy Tachyon on top of Mesos, on top of Yarn, and it's very easy, just one command. And we have an initial like security support as well. As more and more people are using us, this is a very demanding feature. And we have one command cluster deployment, and this is very cool for developers as well. You can deploy a local Tachyon cluster on your laptop, just using one command, or on AWS using one command. It's very easy and fun to use as well. And since people are using this in production, they want to integrate Tachyon with their monitoring system, and we have monitoring support, we have metric support for client, worker, and master, etc. And beyond these features, we have more under storage supports as well. Like you can see these. Some of these are still under development, and we are getting help from many different companies in the industry. And if you want to plug in or integrate your storage system with Tachyon, please talk to us. That'd be very cool. And some like reported Tachyon use case in Fedora channel, in Fedora distribution, default off-heap storage for Spark, exchange data between different computation engine, and people use it in their own product offering. And EMC and Pivotal, they say this is Tachyon will play a critical role in the future data lake architecture. And you have, like, IBM is contributing to Tachyon, writing blogs about it. And this one more thing is that, as Yang mentioned, we also have the company backing this project nowadays, and to guarantee the quality of the project and the fast growing in the project and a lot of more features well organized into a project as well. And it's created by the top creators and top contributors of the project, and we are backed by Andreessen Horowitz, and we are committed to this open source software as well, and that's our company link. And in the end, I'm talking about how to get involved. It's very simple. So this is the stack figure, as you can see. And you are welcome to try the project. You're welcome to contact us. And we welcome any collaboration as well. And you can also just go into the open source community, which is a very friendly environment. And we have new people coming every day. And beyond that, there's some more links, like for your reference. You can go to, you can try. And worth mentioning is that we also have our meetup group. And our last meetup, we have more than 300 people. Talk about, like, last meetup is Baidu's contribution to Tachyon. Like Data, their deep learning framework, doing deep learning on top of Tachyon, and some new features from us as well. And you are welcome to check it out. That's pretty much it. And I'm happy to take any question. Thank you, guys. Okay, so the question is now HDFS allows people to put data in memory as well, and if the workload is only Spark plus HDFS, whether you need to whether it's beneficial to use Tachyon or not, and I think the answer is still yes. So, and here's the reason. So there are several reasons. One reason is, like, Tachyon is future proven. It means that, like, now you use HDFS, and like tomorrow you may use other storage as well. You may use S3, you may have hypercloud as well. So in that case, if you use Tachyon, if you program against Tachyon, it's fine. And no matter what storage you use in the future, it's still okay. And you don't need to do any additional work for that. That's one thing. The other thing is, we take memory. We're memory-centric storage, and we take memory, like we tune our system, and we develop our API, like particularly focusing on the memory performance. And then from performance side, I think we are pretty good. And even beyond that, as you can see, the features I mentioned earlier, all those policies, this and that, that's really easy for the upper layer as well. And we have a pretty good integration with Spark as well. Even though we still have a lot of room to improve, but for example, like off-heap like storage, we are the default off-heap storage for Spark. I think that's the thing, like, if I were you, that I would consider the benefit of some of the benefits, like you add Tachyon into the stack. But in this case, even you add Tachyon into the stack, you don't need to. We still use HDFS in your particular case as the persistent storage, and I think they will work fine. Yeah. Thanks. Any more? Oh, yeah. Okay. So, yeah. So the question is, do we have any benchmark? of like using Tachyon, like with Spark or compare with other systems, this and that as well. So I think along with the development, there are some benchmark posted by developers here and there. But I think what's even more interesting is there's the blog post or talks given by companies which are using Tachyon in production. Say one example I mentioned here is a Baidu use case, like they use Tachyon. So previously, I think they also presented in Spark Summit early this year. So previously, they use MapReduce only, and the performance for a query, it took like 1,200 seconds. And then they migrated the system to use Spark SQL, and that took 300 seconds. So which, like, immediately you got 4 times performance improvement in this case. And then they added Tachyon into this picture, and they further decreased the performance to be 10 seconds, which is another 30 times performance improvement. So I think these are like more important than some vendor benchmarks. Yeah, but I would also say like it's also sometimes case by case. If you have some particular use case you are not sure, you're welcome to contact us as well. Yeah, thanks.
I'm wondering how Tachyon plays together with Tungsten. That does in-memory direct allocation?
Let me repeat the question. So you're asking what's the relationship between Tachyon and Tungsten? Is that your question? Great. So we got this question sometimes. So it's very different. It's very different. So from my understanding, Tungsten is a single JVM memory optimization solution technique. And you can, like other, instead of managing the memory by JVM, by the JVM garbage collector, you allocate your own memory pool inside of JVM. You say, I want to manage by myself. And then you do like some fine-grained management of memory. You don't need JVM. You don't need JVM to do garbage collection. That's Tungsten. But the thing it doesn't address is it's a single Spark performance acceleration. But what Tachyon does is data sharing and management and access. It's at a different layer, and address totally different problem. So in that case, I think it's great to have both technology there. Does it address your question? Yeah, great. More?
Yeah, I think everyone is happy.
All right. I will be around, so after talk. Thank you, guys. Yeah.
So now we'll have a short break for 15 minutes, and we'll come back to this room at 11 for another set of talks, including Spark streaming, how to do data science on SparkR, and also one of the coolest features, IndexRDD.
More busy than graphical I ever thought it would be. Let's hope so. Let's hope so.
least you are having fun.
Yes.
I can see it. Otherwise, it's very difficult to like take it slow. If you are doing
Yeah. That is very true. This is on.
No, well, I'm doing it, and then I will officially start from January 1st. But it's
Yes, I'm. Yes. That's why I'm speaking very lightly. Sorry.
yeah, or you could send me your slide and I'll put it in front of. Oh, okay. Now I remember. Yeah, let's just put definition. Yeah. So I mean, ideally you should try to finish in 25 and then keep like I mean, we can do it. Normal people normally.
That is true. How big is this?
I mean, I guess I'm having
We have to do something we are attending at that? Organizing, hosting, emceeing. Do you have like what about funding and stuff?
Yeah, I mean, so I have startup, some startup. I mean, actually, it's I think one of the best and in terms of students and also like being create my cluster, and then I am started writing. Another interesting business. I think that's really nice because of the like going more
Going
broad.
broad.
Talking about
Random things that do not even make sense. Do they even think deep about it?
they have to make some sense. And then I think the hope is like we will hopefully figure out some students who are good and they will come up with the work. Do you want water? We could use some more.
Yes.
I mean, if you could just deal with
Actually, we could use this table.
Totally. You can't tell.
Yeah.
Okay, let me see what I can do.
this is actually more work than I thought.
A lot of stress. I can totally imagine.
Like
in making sure every person is doing,
yeah, sure.
doing right, no stragglers, making sure stragglers like me who don't send in slides before handling
You are
everyone.
better. Actually, we are not biggest.
So there are other bigger stragglers.
Yeah, I mean, not biggest. But what I'm trying to do is, some reason like people used to see you in a way, like one of their and then yeah, do that people don't really
Morning, Jan.
Is it okay so far?
Well, oh no, I just came.
He just
I
came.
just came.
In terms of attendance, like,
Let's say how many people? Is it around 200?
yeah, 200 plus. Yeah, I think we still needed like 8, 10 registration to break even. And is this the last, or there is one or two more after this? Because I mean, AMP lab is closing in like a year.
Probably at most one. At most one.
Yeah, because I mean, at this level, I mean, one of the things that is happening is that most of the people in the lab, like, previously everyone knew Spark. Now actually no one has storage, Spark, no one knows.
No one knows Spark?
There are many people. I mean, it's not difficult to learn. You can just learn it. It's just that, I mean, one of the good things that is happening, like, I have used, like, Spark for actually trying to try out exercises for after a long time. It was nice that I could just download and everything ran, which was very nice. And it's like, good to have a good quality software that is very nice. You don't have to, like, for trivial things, you don't have to mail someone or something. So, there was someone sitting here, and that lady, beside the yellow jacket guy, yeah, she is probably looking for it. She's very excited about Spark streaming, and she wants to meet me. She thought I am kidding. She communicated with me for a while and mentioning it. I said, yeah, we did it. And then I understood. Oh, I didn't have to go. Yeah, it is fine. As long as they're not saying bad things, I have to
So what's going to happen for AmpLab finishing? Wouldn't there be some sort of a yeah? Like RadLab, I remember there was a big setup of all the things that were developed. Should there be some big demo like in the RadLab ending one day? I think the world has seen everything.
Okay, no worries. Hello? We are going to start the session in 1 minute or two. Please come back and take your seats. We are going to start in 1 minute. Please come back and take your seats. It seems most of the people are back, so we are going to start the second session right now. The first talk will be given by TD, who has created Spark Streaming and sort of manages it. And he's going to tell us what's new in Spark Streaming and what's coming in next few releases of Spark.
Thank you very much, Musharraf. Okay, so you already know, I guess you can guess why I'm called TD from my name. All right. So Musharraf already gave a brief introduction, but something that is worth mentioning is that I was part of AmpLab. So I was there at the first AmpCamp 1 when we organized the first AmpCamp, and it's cool to see how far AmpCamp has progressed in the last 3-4 years.
But it's completely isolated, yeah.
Okay, so currently I'm the technical lead of Spark Streaming and currently a software engineer at Databricks.
Okay.
So what is Spark Streaming? For those who are not familiar, it is essentially a scalable, fault-tolerant stream processing system built on top of Spark. And because it's built on top of Spark, compared to other stream processing systems out there, it provides 3 key advantages over them. One is very high-level API. You get joins, windowing, all these streaming primitives out of the box, which a lot of other stream processing systems do not provide. And it's very concise, obviously, because you've seen the difference between Spark and MapReduce. So more than 5 times less code. It is fault tolerant, obviously, because it's built on Spark. And because it's part of the whole Spark ecosystem, it integrates very nicely with MLlib Spark SQL data frames, and which gives it a lot of power that other stream processing systems out there in open source do not have that sort of power. And so it can take data from Kafka, Flume, Kinesis, HDFS, Twitter, and people are constantly building more and more connectors, receivers, they are called, for Spark streaming, and Spark streaming can push out, process all the data and push it out to file systems, databases, and drive dashboards from it. That's a high-level overview of what Spark streaming is. Now, what can you use it for? And essentially, you can use it for any sort of real-time live data processing. For example, if you have a stream of bank transactions and you wanted to do fraud detection on it, you could use Spark streaming for that. A lot of people use Spark streaming for detecting anomalies in sensor data in real time. Or let's say you are a simple hacker, you want to just do cool stuff like finding cat videos in tweets, you can use Spark streaming for that as well. That counts as big data as well. So the way Spark streaming works is that Spark streaming runs these things called receivers within the Spark cluster. The receivers receive data from external sources like Kafka or Flume, etc., and chop them up into small batches. You can configure the size of the batches. It could be from half a second to few seconds to tens of seconds. You can configure it. And then it gives these batches to the core Spark engine as RDDs to process them. Spark engine processes them and pushes the final result out in batches to external storage systems. So that's the high-level idea. Let's look at how the code looks like of a Spark streaming application. Let's say you want to do a word count on the batches from data from Kafka. So the first thing you need to do is create the streaming context, which is very similar to the Spark context. In fact, it uses a Spark context underneath. And there you specify the size of your batch. So for example, here I'm saying 1 second. And then the next step we do is create something called dstream. And dstream is essentially the core abstraction of Spark streaming, similar to what RDD is for Spark. And and it essentially is a series of RDDs representing a stream of data. So basically, if you have a stream of data, it chops it up into batches, and each batch is essentially an RDD. And this series of batches is represented by a dstream. And you can create dstreams from different sources like Kafka, Flume, etc., based on by specifying the Kafka topic or Flume port or Kinesis stream name. And so the first step is create an input dstream from Kafka. Second step is you apply transformations. You've already seen what transformations look like for RDDs. It's pretty much the same. Here I'm splitting the words, splitting the lines into words. And what happens underneath is that for each RDD of the lines dstream, this transformation flat map is applied to each of those RDDs, creating a new series of RDDs, which is essentially the words dstream now. And now you can do more transformations for doing the counting. And then finally, what we're going to do is, let's say we're going to print some of the counts on the screen. So we're going to say word counts.print. And what print is essentially is like an output operation where you say that, okay, take the final result and do something with it. In this case, just print on screen. And now after the whole, up till this line has been executed, everything is actually lazy. Nothing actually has started processing. All this thing sets up is what needs to be done when data comes in. And to actually start the processing, we take the context and call start. And this is significantly different from the Spark context that you see, because Spark context, you don't start, you just provide actions. Here, you actually have to say start, and now the system will actually spawn all the receivers and start ingesting data, generating RDDs, computing the transformations, and pushing it out to external systems.
How long is TD?
And to push it out to external systems, you can use this basic primitive called for each RDD, where you specify that for every RDD generated by the dstream, do something. You can either save it to HDFS, you can push it out to Cassandra, you can push it out to a MySQL system, whatever you want with the raw RDDs. So that's the overview. Now, besides the standard RDD transformations that you have seen, there are much more transformations that comes out of the box, like, for example, D streams have window operations where you can, for example, this is reduced by key and window, where you're doing a reduction over a window of data of the last 1 minute window of data. And you can specify the window length, you can specify the sliding interval of how frequently the window moves, you can specify all of that. And there are other variations of the window operations for doing window-based aggregations and other stuff. And something, and there's, you can do arbitrary stateful processing in this, and this is a very powerful primitive called update state by key, where what it allows you to do is maintain an arbitrary state for every key in a key value data structure, in a key value D stream. So let's say you have a stream of data regarding activities of a user session. Let's say when a user is logged into a website, you want to build a model of what all the user does while he's logged in on the website. So you can model that using this update state by key, because as data for that user, which is the key, comes in, you want to update the user model and maintain the user model as a persistent state. And this allows you to do that. And all you have to do is write this state update function, where you have to specify for the new batch of data that comes in for each key, the new batch of data, given the new batch of data and the previous state, what is the new updated state. And this function will be applied by the system on every key, and the system will continuously maintain the updated state. So this is a very, very powerful primitive, and the system ensures that the underlying data is fault tolerant, etc., for any executive failures, similar to what you expect out of any RDD operations. And the biggest part is that this whole streaming integrates with the rest of the ecosystem in Spark. So for example, you can interoperate between D stream and RDDs. For example, you can build an RDD from an Hadoop file, and then use that RDD as a static data set against which the stream is joined against. So you can join it and filter out stuff from the stream. Similarly, you can apply machine learning models on top of the stream. For example, you can learn a machine learning model in this example, k-means. You learn the machine learning model using an offline data set, and then use the model to score or predict the live data by using it with a D stream. In fact, you can use SQL, combine this with SQL as well, where SQL and data frames both, where you can, the live data that is coming in, you can query the live data using SQL by registering the data as a temporary table that you can query. So this gives a lot of flexibility on what you can construct out of your system, though that a pure stream processing system like Storm or Samza doesn't allow you to do. So, and as a result, there has been a very rapid adoption of Spark streaming in the industry over the last couple of years. Prominent ones being Netflix, Pinterest, Sony Entertainment, Intel, Salesforce, Uber, they are also using it. So, and it is growing, and this slide is totally out of date. And a recent survey done by Databricks, over 1,400 individuals from 842 organizations, we found that since 2014, there has been a 56% increase in the number of Spark streaming users, which makes it the fastest rising component in Spark. And over these 2 years, as our user base is growing, we are continuously getting a lot of feedback from this community. And that feedback has been driving most of our development in the last few releases. And in this talk, basically, that's what I'm going to talk about, that what are the new stuff that we have added in Spark streaming over the last few releases, and where we are going next. So this new stuff, I'm going to break it up into 3 parts. One, I'm going to talk about the libraries we added, then how we improve the ease of use, and then what are the internal behind the hoods infrastructure changes that we are using to make it easier to use and have better performance. So in terms of libraries, a very key thing that we added in between 1.1 and 1.3 in the last year is continuous learning and prediction on streaming data, basically streaming ML algorithms. And we have added streaming linear regression, streaming k-means, streaming logistic regression. We're going to add more in the future. And what it means is that you have a stream of data on which you can continuously learn, as well as use the continuously updated model to score the data on a different stream as well. And this allows you to build very reactive systems that can continuously learn and adapt based on the current live data. Another major thing we added a while back is add the Python API for Spark streaming. This was added late last year, and we have been continuously improving the API parity between Python API and our Scala Java API. And so we have added Python API for various data sources, all the Kafka, Kinesis, etc. We have been adding that. We have also added Python API for the streaming ML algorithms recently in the last release. And so which makes it much easier for Python users to actually do big data streaming, which currently I don't think there are many systems that allows you to do big data streaming in Python very easily. The other major thing that is going to come in 1.6, which is soon to be released in a month, is improvements to this update state by key. I've already talked about this, that this update state by key takes the key value data and applies this update function to maintain this per key state. What the feedback that we got from the community is that they want to keep a much larger amount of state than we had originally imagined. And the problem with the current implementation of the state by key was that it is the processing time of each batch, basically the throughput of the system, reduces as the state increases, because the batch processing time of each batch increases as you keep more and more state, which is not a desirable performance behavior to have, because you want because users want to keep a lot of state in the system, given though only maybe, let's say, 5% of the state is updated in every batch. You want the system to keep around a lot of the state and not resort to external storage systems like HBase or Cassandra for keeping that state. Also, the users want automatic expiry of keys that have been idle for a while. And based on this feedback, in 1.6, we are adding a new API called track state by key. And the idea is very simple. You provide us this sort of an update function, which has slightly different signature, but it has more flexibility on what you can do with it. But what it supports is it natively supports timeouts, and you can specify the timeout interval, that if something is idle for over 10 minutes, remove that state, because that state is not useful anymore. Because session has timed out, maybe the user session has timed out. But what all the under the hood changes in track state by key actually makes it a lot more performant than update state by key. So for example, if you're looking at the processing time of each batch of data, track state by key can potentially provide an order of magnitude lower processing time than update state by key. And this is a complete game changer for a lot of applications that want to do this sort of stateful processing. Then the second thing we have really tried to improve is the ease of use. And a part of that is we looked at adding new visualizations to make it easier for Spark streaming users to debug. So this is what our earlier visualization before 1.4 looked like, and which was very bare bones, easy to understand, but it was very limited in terms of the amount of information it provided. Rather, in 1.4, we improved it with a lot more information on that provides your trends, processing trends, what is your data rates, etc. All that information is provided as part of the UI itself. You don't have to calculate it yourself. And using this, the user can very easily understand where the system is performing stably or not. For example, for stability, you need to look at the scheduling delay of the batches, whether the batch processing time is approximately less than the batch interval. These are all signs that your streaming application is actually stable. And you can very easily look at it in one glance, whether the application is stable or not. And then what it also provides is details of the individual batches that actually ran, so that if, for example, if one particular batch took longer, this allows you to actually go into the batch and dig deeper that which particular job inside the batch actually took longer, why did it take longer, were there any failures. It allows you to walk through all of that debugging right from the UI. And it also shows Kafka offsets that was processed in that batch, so that if there was some sort of bad data from Kafka itself, you can know which offset range in Kafka actually has the bad data, and you can debug that very easily. We also provided more additional visualizations to show what are the RDDs that are generated underneath, what are the stages that are being generated by D streams, how they related to the D stream operations. All that information is actually showed as this DAG visualization of RDDs and stages. And we are continuously trying to improve that. And the third thing, and I won't go into too much detail in this, but we have added a lot of infrastructural changes, improvements into Spark Streaming. And there are two parts to it. One, and this is totally based on the user feedback and on what the user wanted out of Spark Streaming. One is zero data loss guarantees, and two is system stability. So the system operates in a much more dynamic environment that we saw in different production environments. So zero data loss means that in a lot of streaming applications, the system needs to guarantee that every data that is received by the system needs to be processed and pushed out. There should not be any data loss no matter what fails in the system. And there can be two types of guarantees the system can provide, and that is expected out of a system, distributed system, processing system. One is at least once guarantee, where every record that the system receives is going to be processed at least once. There may be duplicates, but at least no data is dropped. Then there's exactly once guarantee that in the end-to-end pipeline, every record is processed exactly once. And that is important for more mission-critical applications like maybe bank, fraud detection in bank transactions and things like that. So, and to provide these guarantees for a wide range of streaming data sources, we added a lot of new tools into Spark Streaming. And there are two cases for that. For example, for data sources that are not replayable, that is, they cannot replay the data stream that has been received, what we have added is our own write-ahead log or journal, as that is known in in computer science in different places. What it provides is this ability to save the data from the sources and replay it on our own. And I'm going to talk about it more in the next slide. But that's one solution that we have for sources that actually can replay on their own, like Kafka and Kinesis. They can be solved. We have solved them by increasing the reliability of the existing integrations, existing receivers. And again, I'm going to talk about it in the next few slides in detail. So for write-ahead log, the idea is that all the received data is synchronously saved to a fault-tolerant file system like HDFS by Spark Streaming itself, so that if there are any failure in Spark Streaming knows how much data or what data to actually replay to reconstruct what was lost at the time of failure. And it is not enabled by default, but you can enable it by setting the Spark configuration, a simple Spark configuration to true, and setting, specifying which HDFS directory to use to save all this data. And in the end-to-end pipeline, this gives at least one's guarantee that every record will be processed at least once. And this is the solution for, general solution for most data sources out there that does not support replay, but actually has some sort of a ACK mechanism that, okay, this record was received correctly, and move on to the next record. So this provides that end-to-end guarantee. For Kinesis, which is to get the same reliability, what we have added is that instead of saving the raw data, Kinesis records have a unique sequence number to identify the record. What we do is we basically track the range of sequence numbers of the data that has been processed in every batch. And we use that sequence number ranges to actually reconstruct the lost data
and reread it back from Kinesis directly. So this is much higher throughput than using the wall because we're not saving the data. Once again, we are just saving just the metadata so that the data can be read back from Kinesis when needed. And overall, it can give at least once guarantee. For Kafka, we went a step beyond, and we introduced this new API called Direct Kafka Stream. It was in 1.3, and we graduated it in 1.5. And what it does is actually, it does not use receivers at all. It does not use Zookeeper to manage Kafka offsets that is usually used by Kafka users. But instead, it actually does all the Kafka offset management, which is Kafka offset being the unique identifier of records in Kafka. But all managing the offsets, of saving the offsets and replaying them when needed is completely done and managed by Spark Streaming, which allows us to get a much higher throughput than what the previous approach allowed us to get, almost in some cases 10x higher throughput. It allows us to give end-to-end exactly once guarantee, which is necessary for a lot of applications. And also it allows us, this also API allows us to actually run Spark jobs directly out of Kafka, basically treat Kafka pretty much like a file system. So you can read a lot more about the associated links when the slides get published. The second thing that we added is a lot of improvements to the system stability, where streaming applications may have to deal with variations in the data rates and processing rates of the underlying system. For our stability, each application must receive data only as fast as it can process. To do that, in 1.1, we had added static rate limits on the receiver, so that the receivers don't add data, don't ingest data faster than the system can actually handle. But it is the developer's job to actually configure the static rate limit, which we realized was kind of hard to figure out what is the right rate. So in 1.5, we added this new feature called back pressure, where the system automatically and dynamically figures out what is the right rate limit and continuously adapts the rate limit based on the current health of the system. And so essentially what it does is that if, for example, if your downstream sync, let's say you're pushing to Cassandra, and for some reason Cassandra slows down, that would cause the system to automatically figure out that something is slowing down, and which would cause the receivers to push back to the sources that don't send me data faster because I'm somehow slowing down and I'm not able to handle data as fast as you were giving me earlier. So this end-to-end back pressure mechanism makes a system a lot more stable to unplanned or unexpected variations in the system. And it is built, I wouldn't go into the details, but it is actually built on a very well-known PID controller theory that has been there from the 1960s and used in industrial systems to build this sort of adaptive systems. It was contributed by TypeSafe, and what essentially to visualize how it works is that it actually allows, if there are variations, for example, this blue line here is actually the data rate by which that is being generated by Kafka, whereas the system can only process data at this particular max rate. So the green line is what the system automatically figures out. Without any prior configuration from the user, automatically figures out what is the maximum rate the system can handle. And the red line or orange line is the actual ingestion rate that the system is actually taking data in. And as you see, as the generation rate goes down, the system continuously adjusts and caps it to what the system can handle. And what this essentially allows is that the system can ensure that there are very little scheduling delays in the system, and the system can keep up with the data as it's coming in without getting too delayed. And so this is experimental, disabled by default in 1.5. You can very easily enable it. It's a kind of Spark configuration. But in future, we are going to enable it automatically for the users to get more out of the box stability just out of the box. So coming to the final part of my talk, what are the things that we are planning to do next? And this is also again divided into 3 parts in terms of API and libraries. One very cool thing that we are planning to add in future releases beyond 1.6 is streaming data frames. You've already seen from Josh what the capabilities of data frame, of how it actually uses optimizer underneath to optimize the actual physical plan, uses tungsten underneath to do binary optimization of the data. Since that is built on data frames, we plan to build this next evolution of Spark streaming to merge streaming with data frames. So currently, Spark streaming is built on RDDs. The next evolution will be streaming built on top data frames so that we can leverage all the plan optimizations and binary optimizations by tungsten that data frames provide. And as part of that, what we're going to do is add support for event time-based windowing. So, whereas basically you're going to use the data timestamp in the data itself to do any kind of windowing rather than using the wall clock time of this cluster. So we were going to add support for that in streaming data frames, and also support data that is out of order and doing aggregations on out of order data and things like that. In terms of ease of use, obviously we are not done improving the UI. We're constantly adding more and more features to the UI to make it easier for users to debug if there is anything going wrong in the system. And more improvements to the programmatic monitoring. For example, if you want to programmatically monitor whether your system is doing fine or not rather than continuously looking at the UI. So we are adding more and more information to the streaming listener interface that we have for this sort of monitoring so that people can monitor automatically and take actions automatically rather than putting human in the loop. And in terms of infrastructural changes, one big thing we plan to add is dynamic allocation for streaming. And by dynamic allocation, I mean basically elastic scaling, where based on the current load on system, the Spark cluster should be able to automatically scale up and down to handle variations in load in the system. And this is something that currently works for Spark batch jobs, but not for streaming. We want to build the necessary infrastructure for making work seamlessly with streaming, seamlessly work with the back pressure mechanism, etc. And of course, we definitely we're constantly trying to improve the throughput and lower latency. For example, that's the reason we introduced track state by key based on user demand for higher throughput and lower latency. You can read more about all this on our blog post and on a research paper. You can take a look at the links when the slides get published. And that's basically it. So to summarize, it's one of the fastest growing components in the Spark ecosystem. We have really made significant improvements to fault tolerance, stability, etc. And there's lots of features to come, so stay tuned. Thank you very much. Questions? No time for that.
Yeah, so we have time for 1 or 2 questions.
Joseph can start.
Yeah.
I'm just wondering, I think you mentioned sub-second, but from the field, what's the...
Could you raise your hand? I have no idea.
Sorry.
Oh, there.
Typically, what's the smallest windowing size that you would practically recommend today?
We generally recommend something the smallest as half second or so. But what people typically use is around less than 10 seconds. Or I've seen people use the whole range, less than 10 seconds, 5 seconds to minutes to few multiple minutes. So it totally depends on your end-to-end requirements. But the lowest is typically half second. Yeah.
Expect data frames integration at 1.6 or?
Not 1.6. We expect to provide something in 1.7, which is stated to be released around February, March, that time frame. But what you can already do is actually use data frames within streaming programs because it's all underneath RDD, so you can completely interoperate between data frames. Nicer API for more unified API between data frames and Spark streaming would come in 1.7. Yes, one over there. I believe that should be the last question.
Yeah.
Bill Tetzloff. I'm familiar with an IBM system called System S Streams Distillery. Are you familiar with it, and can you compare it?
Not in intimate details, just at a high level. Not in a lot of detail. All right, thank you very much.
Oh, okay.
So our next speaker is Joseph Bradley, and he's going to talk about how to use SparkR and other components to do data science activities.
Great, thanks. Yeah, so I'd like to talk about the machine learning aspects of Spark, but particularly focus on sort of like integrations with popular data science tools from like the PyData and R space. So a bit about me. I'm an Apache Spark committer working as a software engineer at Databricks, but my background is in machine learning. And my Berkeley connection is that I was here for a year, not in the AMP lab, but in Wireless Foundations. But yeah, before I go on, I first was hoping, since it's a bit informal, for a show of hands of people who have used MLlib before. Cool. Okay, and then a second show of hands for people who have used PyData tools or R tools. Cool. So quite a few people, but there will be hopefully something for everyone here. Gonna give a 1 or 2 minute intro of MLlib just to give a sense of what's there, but I won't spend most of the talk actually on MLlib itself. So our goal is to have pretty much a general machine learning library for big data, and that has a couple components. First, we want it to be scalable. You should be able to prototype on your laptop, but then run the same machine learning algorithm on a big cluster on much more data. And in this scaling, it should be robust, where a lot of that robustness, of course, we get sort of for free by being on top of SparkR. We also aim to have coverage of common algorithms, and I'll give a list of those later. But the idea is that we want to be able to cover the majority of use cases, and then for the more specialized use cases, people can either extend or develop their own algorithms. We're also attempting to offer tools for practical workflows. Machine learning isn't just about running logistic regression. There are a lot of other elements in stringing together a practical pipeline, and we're trying to create functionality for that. And the final element, which this talk will be about, is integration with existing data science tools. Data science has been around for a long time, and there are some awesome tools out there. And so we're trying to think about how we can make it easy for people who are from those who are used to using those tools to start using MLlib without some huge gap in between. So in terms of algorithmic coverage in MLlib, here are the algorithms as of 1.5. You can't read them, of course, but let me summarize. At a high level, the set of learning tasks we try to tackle are classification, regression, recommendation, clustering, and frequent item sets, also known as association rules sometimes. But these are pretty standard sets of algorithms within each of these types of tasks. Logistic regression, linear regression, trees and ensembles, and so on. We also try to offer what I'll loosely call data utilities. Everything from feature extraction selection, which is an extremely important part of ML, to things like calculating statistics in a distributed manner, to both local and distributed linear algebra. And finally, I'll group things under workflow utilities. And this includes things like once you've learned a model, you want to be able to export it and import it later for future use, maybe on another system. We also have been working on what we're calling a pipelines API, which is essentially a higher level API for stringing together the many parts of feature extraction, model tuning, different algorithms, and so on in a practical workflow. And a big part of this is making use of the data frames work, which Josh talked about earlier, and sort of writing on top of that work going on in SparkR and Spark SQL, and using data frames as a very flexible data set representation for ML. And the final thing under workflow utilities is a lot of work can go into model tuning or hyperparameter tuning in machine learning. And one very common case of this is doing cross-validation. And so we try to prevent the user from having to write a lot of this rote code themselves, and be able to just do plug-and-play model tuning. But what I really want to focus on is how Spark MLlib relates to existing ML libraries. And I'll focus on scikit-learn and R, largely because of their popularity. So scikit-learn is a Python toolkit which offers a very wide range of machine learning algorithms. And when I think of it, I think it's particularly notable because of its ease of use. You look at its homepage and it has like great documentation, examples, and so on. Very easy to get started. The other one I'll list is R, and I think what maybe comes to mind immediately for most people is like the immense number of packages, which they have, some 7,000. Things like glmnet, which is like one of the most useful generalized linear method packages out there. So given these kind of toolkits, which are great libraries with documentation, guides, packages, extensions, there's been a lot of investment in these. And that means both in education and training, and of course in tooling and workflows, both in academia and in industry. The problem for a lot of people as big data comes along is that these are not traditionally developed for what I'd call the big data space. But of course now people are very excited about this. And the goal here is to do things such as, say, train a topic model on 4.5 million Wikipedia articles, or run recommendation algorithms using millions of songs and users and billions of ratings. And these are actual things which we've done with Spark. The other aspect people look for with big data is to be able to just throw more machines at a problem. Here's a plot looking at scaling with decision trees in Spark, where there are a number of workers on the x-axis and training time on the y-axis, so lower is better. And as you throw more workers at the problem, things just get faster. And of course, the point isn't just to handle a lot of data. The idea is that more data improves your performance in terms of accuracy or whatever metric on your problem. The other aspect of big data, I'd say for machine learning, is that you want to be able to scale gradually with your business. As you get more and more users, as you get more data sources, you want to be able to use the same workflows, reap those benefits without retooling. And the final element, I'd say, which I think is particularly felt by a lot of data scientists, is integration with production systems and being able to bridge this gap between the data analytics part and the production part. So how can we talk about bridging this gap? At school, I studied machine learning on a laptop, but now I want to do machine learning on a huge computing cluster. And so what I'll try to go through is how might you get from a single machine workload to a fully distributed one. And as I talk about that, I'll talk about the various integration points between the single and distributed machine workloads. So first, let's start with a wish list. First, I'd say you want to take your original code and be able to run it in a production environment. And in particular, for machine learning people, I feel like one confusing thing is being able to plug in and immediately use these distributed data sources. The next item in the wish list will be to be able to distribute your workload piece by piece. You don't want to have to do it all at once. Just do it as needed. And a big part of facilitating this will be easily switching between local and distributed settings with respect to your data and how you're running the computation. And the final item I'll list is being able to use familiar APIs. If you have a workflow, you want to have recognizable algorithms which you can switch to when you need to distribute things. You want to be able to have similar parameter settings so that you can, since you've done tuning in a single machine setting, you can take some of that knowledge to the distributed setting, and so on. And so to demonstrate this, what I'd like to talk about is a very simple task. So here's a chunk of data from a set of Amazon reviews. There are two columns. The first one is ratings from 1 to 5, 1 being bad, 5 being good. And the second column is the text of the reviews. People are reviewing these things they bought on Amazon. and they like them or they don't. So I'll call this sentiment analysis, where our goal will be, given text, we want to predict whether or not the person writing that text, is happy or upset. And then the idea is, when you see new text, which may not even be a review, maybe it's a tweet about a product, you'll be able to apply this model and predict the sentiment. So let me describe the workflow, just to give you a sense of, especially if you're new to ML, the types of tasks you want to address in an ML workflow. So in this simple workflow, we'll start off with text and ratings. We're then going to pass it to a tokenizer. And the idea here is that we have this text, which machine learning algorithms don't necessarily know how to handle. So we're going to mush it into a nicer form. Tokenizer just means split it into words. So now we have a set of words. We next pass it to what I'll call a hashing term frequency module, which hashing refers to taking these words and hashing them to a fixed length numerical vector. And term frequency is just a text-based reweighting scheme. So what we've done here is taken our raw text and converted it to a nice numerical vector an ML algorithm will understand. And the actual algorithm we'll use is linear regression. And once we've trained that model, we'll be able to make predictions. Say on this text, we push it through our feature extraction, make a prediction using the linear regression model, and get some rating. And at the end, we can compare that prediction to the true prediction in our data. Cool, so these are sort of the three elements, and I'll lump them together into feature extraction and model training. Cool, so here's our very simplified ML workflow: feature extraction, model training. The other aspect of ML is model tuning. And here the idea is that these algorithms may have a number of parameters. Here I'm listing a regularization parameter, which essentially tells the model how much it should trust the input data. And the idea is that if it trusts it too much and overfits on it, then when you see new data, you'll make bad predictions. And so adjusting these kinds of parameters in ML algorithms can significantly change the performance. So to choose them, what we do is choose them in a data-specific way using what's called cross-validation. And basically, the idea is that you train a bunch of models, model 1, model 2, model 3, using different parameters, test them on held-out data, and then at the end, select your best model. Cool, so this describes our very high-level basic ML workflow. And what we're going to talk about first is how we can start distributing it. We'll start off just running everything on one machine. That's what I mean by the little red canister. But of course, you can immediately see one nice thing we could do, which would be, say, we're training a bunch of different models. Why can't we just train them in parallel? So we'll do that. We'll distribute the cross-validation, where each of these will train on a separate machine. So what I'd like to do is break out into a notebook and may need to do a bit of resizing, but all right, so what I'm doing here is showing a notebook, which this is a Databricks notebook, but all the code which I'm showing can be run just in open source. But this will be nice for the sake of describing this workflow. So we're starting off with a simple workflow, and it's going to be in scikit-learn. So I'm importing some stuff. I'm loading some data, and now let me look at this data. So this is the same data you saw before. Have a list of ratings, have a list of review text, and it's in a pandas data frame. By the way, I'm running this on a 10-node cluster, but this code I'm running currently in scikit-learn and pandas will be running on the driver. So we can look at this and say, okay, we have about 20,000 reviews, and we can take out the reviews and ratings in formats here, which will be nice to pass to scikit-learn. So our next goal will be to train a scikit-learn model. And now you don't really need to go through and understand each of these elements, but you can recognize the elements from the slides before. Hashing, the TF weighting, lasso, which is a type of linear regression, and in particular at the bottom here I'll highlight 3 possible parameters which we're going to tune using cross-validation. Okay, so we specify that workflow and the set of parameters to scikit-learn. And then what we need to do is run cross-validation. So scikit-learn provides this nice thing, grid search CV. And what this does is take the pipeline, parameters, a number of folds of cross-validation, and what it's going to do is for 3 iterations, it's going to take some part of the data and leave out another part of the data. Then for each of our 3 parameters, it's going to train 3 models on this set of data and test on the held out set of data. And then at the end, it's going to find sort of the average results for each of the possible parameters and choose the best possible parameter. So in this case, it's learning 9 different models, took 27 seconds, and great, now we have a model and can make predictions. So what I'm doing here is computing a score, and if you're familiar with it, it's the R-squared score. But basically, it's a score where lower is bad, higher is good, and in this case, we get 0.14. We can do things such as, say, evaluate on test data. Here I'm loading a new set of data and testing on it. And what you can see here is sort of our first integration, which I hid at the beginning of this workflow. If you notice, I'm loading this data from using a SQL context, and in particular from our Parquet format, which is like this nice distributed columnar storage. And then I'm using a Spark SQL method called toPandas, which just nicely converts this Spark data frame, which it loaded from Parquet, to a Pandas data frame. And then I can pass this directly to the scikit-learn model. Cool, so we see we got our squared score, 0.13, and so on. And of course, if we had more time, we'd train on more possible parameters, et cetera, and see about improving our predictions. The other integration I'd like to see show here is the reverse direction, where say we want to take our predictions and store them in a Pandas data frame, but we want to save them for some production users later down the line. And in order to do that, we can immediately convert that Pandas data frame to a Spark data frame and write it out to, say, a JSON file in, here it's a mounted S3 bucket. Cool, so I just did that. And what this demonstrated was largely conversions of data frames between Spark and Python Pandas. Cool, so if you recall though, what we were doing with model training was this cross-validation step where we were training 9 different models. And of course, the natural thing we'd want to do is parallelize this. So let's do it. And what I'm going to demonstrate is a Spark package which we've been working on, which attempts to emulate scikit-learn's API very closely. So I'll go here to our imports, and the one thing which I will do is first, okay, sorry, I had forgotten to do this. I'll need to attach a library to this cluster. And once it is attached, I'll be able to import a grid search CV class with the same name, but okay, cool. I think it's attached. So with the same name as the scikit-learn one, but which will essentially do the distributed computation and hide the difficulty of it under the hood. And for this, I'm essentially going to do exactly the same thing, except that at the end here, where I do the actual grid search cross-validation, I'll give it a Spark context so that it can distribute the computation. So what this is doing is same thing as before, 9 different tasks, but it's running them in parallel. And it'll be a tiny speed up here, but of course, as you scale this out, it'll be even more significant. So before it took 27 seconds, now it's 12, but you get the idea. Cool, so now what we have is this grid search object. And what it's going to offer, if I recall correctly, is an sklearn model. And so what I'll do, just so we can retain the rest of our workflow, is just extract that sklearn model from the grid search, and then we can do everything else as before. So we get the best estimator out of the sklearn model. We can compute, say, the score on our data, and so on. So what was this doing underneath? Well, the idea is that we're able to run scikit-learn jobs on workers in Spark and use Spark to coordinate those tasks. And I have more notebooks, which will be linked in these slides, but probably don't have time to go through them now, but I'd like to describe what they demonstrate. Basically, as you scale up, you can start to hit other bottlenecks and start to distribute those. The next thing that the notebooks demonstrate is distributing feature extraction, where rather than doing everything on a single node for feature extraction, you may have a complex set of algorithms there and, say, want to split it up across different nodes. And what the notebook, which I won't have time to show, demonstrates is doing this distributed feature extraction using Spark, but analogous methods to the scikit-learn ones, collecting the results back to a pandas data frame, and then doing what we just did using scikit-learn jobs in Spark workers and coordinating those via Spark to do this distributed cross-validation. Then finally, at the end, getting the scikit-learn model back. And then the final element, or notebook, will show completely distributed learning using just Spark, where we keep everything distributed, including training individual models. And this lets us scale up to even larger data sets. Cool, so I'll just quickly step through the wish list again. We had talked about running code on a production environment. And basically, all that was needed there in the case of Spark was being able to run Python code on the Spark driver. But what let us use those data sources were the data frame type conversions. We also talked about distributing the ML workload piece by piece. And we started with cross-validation, where there's this Spark package, which essentially just ran scikit-learn tasks on the workers, but had some nice API to hide that complication. We next distributed feature extraction, where the key thing there was converting between vectors and matrices between Spark and SciPy. And this is in one of the notebooks I didn't have time to show, but you could look at later. And then the final notebook, which again I didn't show, is just using Spark, where we finally distribute model training. So the final element in our wish list was using familiar APIs. And there, with a Spark package for scikit-learn integration, our main idea is to minimize modifications that the user needs to make to code. And with respect to MLlib, trying to have similar functionality and workflows as in other tools like scikit-learn. Cool. So I'll just quickly mention that some of the improvements we observed, if you go back and inspect some of the notebooks, are first faster model selection when you have a smaller data set. Then when you scale up to even larger data, faster training. And then finally, better predictions via that R-squared metric with more data. Those are in that final notebook. And in practice, you get even larger problems for many reasons. Use more folds of cross-validation, tune more parameters, and often you increase your model size or complexity as your data grows. So to repeat this at home, this demo is using Spark 1.5, and this PD-Spark package, which will be released very soon. The demo notebooks will be linked from the talk slides. And I'll also mention there's another scikit-learn integration package, which takes a somewhat different tack, but again, is trying to make a familiar API which can still leverage Spark. So you could check it out as well. So I've been focusing on the PyData space, but also want to mention integrations with R. First, I'll mention data frames, where just like with Python pandas, we have conversions between R local and Spark distributed data frames. And using Spark data frames from R, you can make SQL-like queries, as well as queries using familiar R-like APIs, such as this. Here it's saying, let's look at this data set. I think it's an Old Faithful data set, and look at the set of eruptions where the waiting time was less than 50. The other element of the R API is providing access to the distributed implementations of ML algorithms. And so currently, the only coverage we have are for linear models, like linear regression, logistic regression. But we're trying to follow an API very similar to what our users would expect. Here it's saying, let's model the sepal length of a flower by these other aspects, giving it a Spark data frame. And this is the same syntax you would expect from popular R packages. Cool. So finally, I'll just end with mentioning a bit about what's coming. So in 1.6, there are a number of new algorithms in MLlib. Survival analysis, online hypothesis testing, more feature transformers, faster clustering algorithm, and the ML pipelines API, which is really cool and useful to a nice API to build complex pipelines. One of the final things which we're adding is persistence, where you can save and load pipelines. We're also providing more statistics for models and expanded API coverage there. There are also improvements to data frames with stats functions, R formula, and documentation. And the final thing I'll mention is, in terms of the roadmap, what we're really trying to focus on is completing out these APIs, providing more summaries and statistics expected by people coming from, say, R or other toolkits, and also ease of use, doing more things implicitly when possible, providing nice APIs like R formula, and improving documentation. Cool. And with that, I'd like to thank you. And yeah.
We have time for one or two questions. Okay, I guess everyone is very happy with what they have seen.
Good. Good.
Thank you.
Yep.
So our next and the last speaker of this session is going to be Ankur Dave, and he's going to talk about IndexRDD, how to do fine-grained updates on RDD.
All right. Yeah. So as Musharraf said, my name is Ankur. I'm a grad student in the AMP lab, and also a Spark committer and a maintainer of GraphX. So I'll be talking about supporting fine-grained updates to RDDs, and the motivation for this work was GraphX actually, where we wanted to add vertices and edges to an existing graph. So we never actually ended up releasing that, but we did have this package that does that, and we think it's a broadly useful package, and that also brings together some interesting research ideas. So the background is that Spark allows users to build data sets, which are these parallel collections of records, and it lets people manipulate them using data parallel operators like map and reduce, or using SQL-like operators. And then Spark executes these transformations by breaking them up into tasks that run concurrently across the cluster. And the key thing is that each task executes independently on its input records and produces separate outputs. Now, Spark is meant to scale to large clusters where hardware failures or software bugs can happen in the middle of a query. So one of the key points of Spark and the predecessor systems like MapReduce was that they recover from failures by rerunning just the failed tasks without having to restart the whole query. So here, for example, if map task 2 fails, then it'll just be retried and everything else can go on as normal. So that avoids wasting resources on rerunning large queries. Also, some machines might have transient slowdowns from multi-tenancy or GC pauses. And so there's this feature called straggler mitigation, which can optionally launch speculative duplicate copies of slow tasks and then use the output of the task that finishes first. So here, for example, map task 2 is really slow, and then at some point it gets duplicated, and then the replica finishes faster. So both these features, the fault tolerance and straggler mitigation, require that each time a task is run, it leads to the same result, regardless of what else has happened in the cluster or on each machine. So that is this key property of task replayability. And Spark ensures that by requiring each task's input to be immutable, so RDDs are immutable, which is basically just done by copying the input before updating it. And also that tasks are deterministic. Now that's something that users just kind of have to do on their own, but it's partially guaranteed by making tasks single-threaded. So that eliminates a lot of concurrency, sort of non-determinism from interleaving. So immutability is the best way to ensure that Spark tasks are replayable. But people are also starting to use Spark for a widening range of applications. And a simple example is streaming aggregation, where we have a series of events, like one Twitter user following another, and we want to maintain some aggregate for each category, so something like a follower count here. Another example is just this broad class of incremental algorithms, where we have a stream of updates, things like new vertices and edges in the graph, and we want to do some incremental computation each time the graph changes. So Spark is a compelling platform for these applications because they often fit into a larger pipeline where the other operations are bulk transformations, like loading data or performing ad hoc queries or machine learning. But these applications don't fit into the bulk transformation model because they require these efficient fine-grained updates. So there are some obvious solutions that you just immediately think of, but they each have significant problems. One obvious solution is just to apply updates by modifying the data sets directly in memory or on disk. And that's fast, but comes at the cost of fault tolerance, because task failures will just corrupt the data by leaving different keys in different states. So here's an example where there's a task that does something simple like incrementing these two shared counters, x and y. And so if the task runs partially and then fails, then it can leave the state in this inconsistent state where you have x and y are different. And then even retries may just compound the failure. So a better option is to move data that has to be updated from an RDD into a transactional database that supports atomic batch writes. And in fact, Trident, which is sort of storm system for getting exactly one semantics, does this directly. And also a research system called Naiad implements a similar system, its mechanism by using logging and checkpointing. But a common pattern in Spark is actually performing different computations on the same base data. So for example, extracting both the top ads and the most popular pages from the same clicks data set. So this kind of a thing where you want to reuse the same data and apply incremental updates to it in different ways is something that it's tricky to support. So in theory, databases that support multi-version concurrency control can do this, but they would need to take a consistent snapshot of the base data set before launching any task and preserve the snapshot for as long as the data set might be accessed. And this kind of a feature is pretty uncommon in databases and hard to support efficiently. Also, it complicates parallel recovery when in the presence of mutable state, and that's one of the key features of Spark streaming. Yeah, so this is representing how long you have to keep a snapshot alive if you want to do updates in this way. So okay, so what Spark currently does is just to copy the entire RDD before updating it. And that makes sense when most or all the records are being changed, which is the common case. But for sparse updates, which are there in these applications that we want to support, that's very inefficient. So there seems to be this trade-off between immutability for fault tolerance on the one hand, and straggler mitigation on the other. For immutability for fault tolerance and straggler mitigation on the one hand, and supporting fine-grained updates on the other hand. So the question is it possible to get both? And it turns out it is. There's this class of data structures that supports both immutability and efficient updates. And these are called persistent data structures. Now, this is named after the concept of persistence from the programming languages community, where persistent doesn't mean stable storage. It means that past versions stay around even after updates, kind of like Git. So here, persistent data structures support these efficient versioned updates that create a new version rather than modifying the existing one. And updates do that by returning a new copy that internally shares almost all of the structure of the existing copy. And that's easiest to do when the data is organized into a tree, because then updates only need to allocate a small fraction of new nodes. So you can kind of see that here we're modifying some leaf node and just copying a few nodes, and everything else remains the same. So we created this persistent index data structure in Java called part, and used that to implement a new kind of RDD called IndexRDD. So IndexRDD supports, it stores key value data, and in addition to supporting all the standard RDD operations, it can be efficiently updated without having to do a full copy. Also, it uses part to support some new fast operations, like really fast point lookups and pre-index joins. And it does all this efficiently, and you can see in reasonably little code. Okay, so here's how it works. RDDs normally store their contents in an array for each partition within like the block manager or the cache. And IndexRDD just uses this special data structure, this part data structure, instead of just an array. And everything else remains the same. So keys are still partitioned using the standard hash arrange partitioning. Updates are still stored in the lineage, which acts like sort of a write-ahead log for fault tolerance. And updates also return a new IndexRDD that reflects them. So this whole thing builds completely on top of Spark, so it interoperates with batch computations. And then finally, here's what the interface looks like. So first, just from the signature up there, the extends, you can see that IndexRDD will support all of the same operations as any pair RDD for any key and value type. But there is one restriction, which is this key serializer, which basically says that the key type has to be serializable. And we'll see how part uses this for indexing. Okay, but so now this supports things like get and multi-get, these things that aren't really efficiently supported on RDDs. It adds this functionality, and it does that by running tasks on the appropriate partitions and then just fetching the results out of this special data structure. Also, it supports updates, so put, multi-put, delete, again by modifying the appropriate partitions using the data structure and then returning a new IndexRDD. And also, it's important to note, these work just like any other RDD operations in that they can only be called from the master. So you kind of have to go through the master to do updates. And the reason is that there's lineage that has to be maintained. And also, IndexRDD re-implements some RDD and pair RDD operations like filter and also a number of joins to take advantage of the indexing. Okay, so now let's just take a look at how this index data structure works. So the starting point is some work from databases called the adaptive radix tree. And this is a trie with a high branching factor. And, it's a trie with a high branching factor and with this feature called node compression. So this choice of branching factor of 256 is just a simplified tree operation. So you just need to address each byte of key rather than shifting and masking. And then node compression is that to reduce space usage, nodes change representations based on their sparsity. So that's the number of non-null children. And then these representations are carefully chosen to keep the traversal speed high. So like I said, this is prior work, and that's just the starting point. But first, you might wonder, why are we picking this radix tree? Why not like hash table or B tree, which is which would be more common choices for indexing? So there are a few reasons. One is that unlike hash tables, radix trees store keys in sorted order, so you can get fast range scans using in-order traversal. Second, compared to binary search trees or B trees, radix trees have better asymptotic performance for long keys. And again, the reason is that they exploit the key structure, because each comparison in a binary search tree kind of only gives you back one bit of information, which is, is it less than or greater than the thing I'm comparing to. And whereas each comparison with the radix tree can eliminate a lot of keys, like up to 255 out of 256 keys for each comparison. So there's this asymptotic difference. Also, there are these nice specialized operations, and this is actually the reason that we originally picked this data structure. It's that it supports these very efficient union and intersection operations. And again, it lets large numbers of keys be illuminated based on their prefix structure. And then finally, there's sort of this ideal of predictable performance where there's no rehashing or rebalancing that has to go on. And so, in a sense, there's more predictability than the alternatives. Anyway, so now here's how we actually take this radix tree data structure, this adaptive radix tree, and get persistence, which is get efficient updates and immutability. So we use the tree structure to make sure that a single modification won't require a full copy, as I mentioned, and instead, when a node is modified, we just have to copy the node that is affected and make the modification, and then copy all the ancestors up to the root to reflect that pointer update. And then also, you might be worried about the tree height. Like if the trees are really deep, then you might end up with a lot of copying going on. But actually, well, first of all, the tree height is kind of logarithmic in the size of the information stored. And also, because of the high branching factor, it ends up being pretty small in practice. Okay, so we implemented this in C++ and Java, both. And I'll show some benchmarks of these things later. But also, in addition to path copying, each tree node maintains a reference count so that old versions can be removed while new versions still reference parts of the data. And that also helps us, that lets us lets us do garbage collection in C++. And there's one kind of key optimization, which is that in some cases we can actually perform updates in place and avoid all this copying stuff. So in particular, updates to a version that will immediately be discarded can be made in place when they wouldn't affect anything else, any other versions. So here's kind of this figure that tries to illustrate this. So suppose that then you have two versions of this part data structure, two different dictionary data structures, V1 and V2. And suppose we want to update V2 to create this new version V3. Then if V2 is never referenced after that, and if the update only applies to the nodes that are only referenced by V2 and not the V1 nodes, then that can actually just be done. It's equivalent to making the update in place in V2 and then just calling it V3. So anyway, so this is kind of the thing that gives this data structure a lot of its performance. Okay, so here the next thing I'm going to do is try and show that the performance and memory efficiency of this data structure are competitive with the standard mutable data structures, despite being immutable and giving this huge feature of versioning. So what we did was we compared this part data structure against some mutable things, a mutable hash table, mutable red black tree, and mutable B tree. And these are all C++ just for ease of benchmarking. So we loaded each data structure with sort of a sample, a benchmark set, and then made some random updates. And so here you can see that for small batch sizes, which is when you're frequently getting back a new version, then this data structure is kind of forced to do a lot of copying, and so its performance isn't quite as good as those mutable data structures. So hash table, for example, gets 800,000 of these updates per second, whereas in this case we only get about 100,000. But as the batch size grows larger and kind of the cost of having to create this new version gets amortized across more updates, then the performance of this part actually starts to exceed mutable data structures, even despite having this guarantee of versioning. So this is kind of a remarkable and nice thing. Okay. Also, these are just the kind of other useful benchmarks. So how fast are lookups, for example? Turns out they're pretty fast. They're competitive with hash tables. Scan performance also is pretty good. Not quite as good as a B tree, but and then memory usage again is comparable with these. Now one thing was that to improve the scan performance, we were a bit concerned about this because scans are a really common operation in Spark. So if they're slow, it'll be bad. So we actually wrote this custom allocator that arranges nodes in the scan order when possible. And so that sort of does a slightly better job than the default C++ allocator and gives us this 3.6x improvement. Okay, so there's the first line is kind of the default allocator, then we were able to get from 11 million elements scanned per second to 40 million. And then there's this optimal, which is factor of 4 or so more away. Okay, and also one other thing is that checkpointing is an important thing that Spark does often. So if you have this long lineage, then it ends up being important to checkpoint it every so often, so that you can kind of bound the amount of time that the Spark will take to recover in case of a failure. And so since this is also an important operation, we wanted to make this fast. So we came up with this slightly interesting trick of incremental checkpointing. So the idea there is that we can sort of use a tree structure to track where the changes are happening, and if changes kind of don't touch some large part of the tree, then we can avoid having to rewrite that tree out to the checkpoint, and instead just reference the previous checkpoint. And so this is some analysis for that. So the conclusion is basically that the blue line is representing a uniform write distribution. So if the updates are kind of happening all over the place with no pattern, that's the worst case for the scheme. But even then, if you update kind of fewer than 1 in 1,000 elements per partition, then this ends up giving a good 10x or more savings of checkpoint size. And then in the more realistic case, when updates are skewed, then it actually helps quite a lot, even for much more frequent updates. Okay, now finally, we kind of put this together in an end-to-end application. Here's a benchmark of it. So the idea was just to do streaming word count, where we're synthetically generating some words that we wanted to count, and then passing them through either Spark Streaming or Cassandra or our thing, or a kind of a upper bound, which is a C++ hash table that's mutable and has no fault tolerance. So that kind of provides weaker guarantees than anything else, but it serves to show what we could possibly do. So here you can see that it's log scale. So you can see that we're, first of all, outperforming Spark Streaming by a huge factor. And the reason there is that Spark Streaming, like I said, has to copy the entire in-memory state for each update, no matter how small the update is. So if only one word changed, or if only one word came in, and so we only want to increment one row in the word count table, then we'd still have to copy all million or 100 million of these word counts. So that's the reason for Spark Streaming's performance. And Cassandra does reasonably well. So, but it has to write data out to disk for one thing, and also it's not. Yeah, I mean, let's just suffice to say that even despite batching and other optimizations, it ends up having to have some unavoidable overhead that makes it not quite as fast. But then the real thing is that we're actually able to get within sort of 18% or so of the upper bound of the hash table. So that was also pretty, we were happy with that. Okay, so finally, this thing isn't perfect, so there are a few limitations. One of them is that in the Java version, which is what is actually available for Spark, for very large data sets, you can encounter GC pauses, which will hurt predictability. So there's this idea, which is that we already maintain reference counts for each node for our internal use, and so we actually could use these to do garbage collection off heap, and also could use object pools to control memory fragmentation if we did this. So that kind of ties into Project Tungsten, which is to move more things in Spark off heap. And secondly, in cases where there are long keys that have high skew, that could actually artificially increase the tree depth. And I can go into this in detail maybe if you're interested. But in this very special case, there are other alternatives that would be better, like a copy on write B tree. Okay, so it's kind of the one high-level takeaway that I think this research came out with is that efficient updates to immutable data isn't a contradiction. You can actually have both. But also, this is a Spark package, and you actually can use it. So there's this exercise after lunch that will let you try it out. Okay, so I'm happy to take questions now. Okay, so the first question was, does this inherit from any existing Spark component? And so the answer is, currently it just sort of depends on the Spark core because it extends RDDs. So there's a number of other packages that do that similarly. But it'd be nice, we're interested in having this work for Spark SQL. So to work as an index that you can just turn on for a data frame and then let you, make updates to the data frame. So that would, in that case, be for Spark SQL. The second question was, was whether we've considered using this for aggregation in case of like if you're doing OLAP. So if you're scanning some big data set and then on the fly computing some aggregate, then so the answer to that is so in that case, I think versioning wouldn't be as useful because like you probably don't care what the aggregate was for some partial subset of the data. And in that case, Spark actually already has like the shuffle component, which kind of ends up doing a similar thing internally. And so for these kinds of internal use cases, it's probably more efficient to use the conventional mutable data structures. But where part comes in is when the user actually has to get back some version data and then kind of wants to be able to have access both to an old version for maybe reasons of applications or because of the application or because of fault tolerance, and also to the new updated version.
Any other questions? Yeah, so I mean, we can, I guess, again, thank the speaker and then move on. So with that, we are at the end of the second session, and I have some announcement to make, and then we're going to go for lunch. First of all, lunch is outside, and it's a beautiful day today, so you can have lunch here, go outside, go to the other spaces in the International House. And when we come back, we'll be having exercises at 2 p.m. For the ones at the back who don't have any desks, we have 2 other rooms upstairs with desks, so you can actually put your laptop down to do the exercises. And one more note regarding the labs and exercises is there are some USBs that you will see in the swag table. Those are souvenirs, and they don't really have any content. And the ones who have downloaded, you already have the stuff. The ones who haven't downloaded, we have much faster USBs that we'll be using just when we start the exercises to quickly copy the data. With that, I look forward to seeing you again at 2 p.m. Thank you.
I would just like to mention that the patio is when you walk past the restrooms, then you'll take the stairs up, and that's where it's probably the nicest place to enjoy your lunch.
Okay, that would be
the entire time the watch are here, so
that would be great.
I don't know
if someone is around.
Yeah, I really don't know who's.
I mean, it's not mine. I borrowed it from someone else.
Okay.
Yeah, maybe I should just take it.
Just
Yeah. 3 locations. One is here where you can sit down and go on with the exercises, and we have 2 other rooms. If you don't have any space with a desk in front of you, you can go down the lobby and go upstairs. There are 2 other rooms with desks where you can sit down and use your laptop instead of putting it on your lap. And in terms of exercises, they are already online. If you go to AMCAM6 website /exercises, you will see them, and there are in total 10 of them divided across 9 different topics. And we are planning to go over up to 5, and then if you are going too fast, you can also try the other ones as well, and you can actually go out of order if you want. It doesn't really depend on something else you have to go through. And other than that, we have to make sure that all of you have the content that is required to run these exercises. So there is a link to this zip file with, I think, something -rc3.zip file that has all the content, the latest content. And some of you have already downloaded it, which is fine. And those who haven't downloaded, we request them not to try to download it over the Wi-Fi. We have TAs with USBs with them. So if you sort of raise your hand, someone will come and help you. And once you are done, if you give it back to us, so we can give it to someone else as well. And other than that, I think we are more or less good to go. Thank you. Just to get a sense, can you please raise hand one more time, like those who don't have the data? Okay, thank you. If you still haven't received a USB, please raise your hand. I think we are all set. Hi, everyone. We are at the end of the exercise session. I mean, you can still continue. We'll have talks from 5, and from now to 5, you can go out and have something to drink or something like that, or just stretch your legs, I guess. It's been a long session. And I want to apologize again for the people with Windows. Like, some of them had really hard time, and I'm very sorry about that. And I hope for others it went smoothly. Thank you. Hi, everyone. We are back for the very last session of today, and to start it, we have Shivram, who is going to talk about a very recent project called Plank, where he's going to talk about how to figure out what types of instances to use to do different types of workload that optimizes your cost or some other metric. And that's all. Yeah, he'll give you the details.
All right, just hit play, and then we'll just switch it here once you're ready. Cool. Give it a sec. There we go. Is that? Oh, you know what? It looks like you're gonna have to read it.
Nope.
It just didn't like the connection. Oh, what? Simulator resolution is that? Power.
Oh, sure. Still doesn't like it.
Yeah, it still doesn't like that.
Should we try the other cable?
We can, yeah, absolutely. Well, it's essentially the same. Let me see one other thing real quick. Oh, you have a lot of desktops open too.
Can you close the other ones?
Let me just do. Okay. Let's try. We may have to. Yeah, you have too many. I think what we're gonna have to do is just close
Sure.
your desktop.
Yeah, let's do that. Let's get them all of it.
Okay, cool.
All right.
And then it may.
It may have other desktops on the other top.
Okay, cool.
I don't know. Like, I don't know how to figure that out.
And it may need a. Let me see 1 second, please. Let's keep that reconnected. Okay, let me just see your resolutions real fast. Okay, this is great. This is great. And then it's not popping up with the options. Okay. I think if this is not doing it, then
The other thing I can do is not use the presenter view and see if it works out. Let's do this.
Just go to mirror.
Mirror, yeah, let's just mirror the display and I'll be fine. Alright.
And you probably could display it at 720, but if you want to just start.
I'll be fine. Still doesn't like, no.
I would kick down your resolution to 720. So get a scaled, go down to. There you go. Now you're up full.
No, I just needed to not have the presenter view. I just need to convince PowerPoint.
Just play and turn off. And then you go to, you go back to, yeah, you just give them the other one. So you go to exit, you go to presenter, setup, where is it? Go hit this drop down, the drop down. And then is it settings? Broadcast slide.
could also use another computer. I don't mind switching to another laptop. Marshall?
Do you want to try restarting it while we wait for the other one?
Marshall, can I just try your laptop? Was that the one people were using in the morning?
We've been using a couple different laptops so far.
Okay. I'll just email them this one. I sent you a PDF like just a little bit back, but I mean, there's also PPT that I'm just sending right now.
Cool. I mean, one of the things you could do, like, to put this thing on Dropbox while connect us, or like, have you just sent me?
I just sent you an email. Oh, you don't have Wi-Fi?
The Wi-Fi is to your Gmail.
All right, so we got something to work. Sorry for the delay. We had to switch some computers and laptops to get the displays to work out right. Hi, I'm Shivram. I'm a PhD student in the AMP lab, and today I'm going to be talking to you about some very recent research that we've been doing called Plonk, which is a performance prediction engine for large-scale advanced analytics. This is joint work with Zhong Heng, who is an undergraduate researcher at AMP lab, and professors Mike Franklin, Ben Recht, and Jan Stoika. So if you take a look at some of the workload trends that we're seeing in data centers, we see a shift from some of the more traditional SQL-style workloads to some of the more advanced, what I like to call as advanced analytics workloads. So what do I mean by advanced analytics? So these include things like machine learning workloads that you might have heard talks of or you're going to hear talks about tomorrow. Machine learning workloads including, for example, like image classification, where you want to detect cats that are there on the internet, or speech recognition, where you want to talk into your phone and you wanted to identify what you're talking. But it's not just in the consumer space. Even in like scientific applications, we see a lot of these sort of big data, advanced analytics things, which are sort of becoming deployed more and more on commodity machines. So this includes, like, for example, the astronomy data sets, where we have like huge amounts of astronomy data being processed to detect stars or like supernova and stuff like that. But also like MRI data and other like mass spectrometry imaging, where again, large amounts of data are being collected in the physical realm, and we want to do a lot of advanced analytics in processing them. You might also see this trend shift if you've been coming to the AmpCamp for the last 4 or 5 years, where in the first few editions of the AmpCamp, we mostly had SQL and like ETL-based talks, whereas in this edition, we have a large number of like machine learning-oriented talks. So we've also seen a trend like this in the lab and in the kind of projects that we work on in the lab itself. One of the projects that I've been very closely involved with is this project called Keystone ML. You'll be hearing a talk about it in detail tomorrow, but at a high level, Keystone ML provides an interface or a framework for doing large-scale machine learning. So when we talk about advanced analytic workloads and we talk about like how we're going to like build them and how we're going to deploy them, one thing that's useful to understand is how do these workloads look? What are some of their properties? So this is an example Keystone ML pipeline that I've shown here, which is used, for example, in like speech processing applications, and similar patterns exist in other applications as well. So what happens here is we take some raw data. This could be images, or this could be like audio samples you have, or some text fragments you have, etc. And then we apply a series of featureization steps. So in this case, we are applying, for example, a cosine transformation, or we're doing some feature normalization after doing cosine transformation. And after doing some featureization steps, we typically use a learning algorithm. So in this case, we're using a least square solver, which is going to learn a model based on the training data that we have. And it's not just like one iteration of these things usually give us a good model. Usually we need to do a large number of iterations of these workloads in order to get a high quality model. So for example, some state-of-the-art work which builds a very good speech recognition model repeats the same pipeline that I've shown out here for around 100 iterations or so, and it could take many hours or so to run to get a very good model for the data set that we have. So if we take a step back at these workloads and try to see what is different in these workloads when compared to more traditional workloads, one observation that we make is that they're more numerically intensive. So they deal with more large number of like floating point operations and other like matrix or linear algebra operations as a part of like these workloads. They're also iterative, so most of them run a really large number of iterations, and each iteration is not just like one job. Each iteration could span many jobs. So for example, in this previous slide that I had, each iteration runs like a cosine transformation and a feature normalize, etc. So you have a complex DAG that's getting executed on each iteration. And finally, as a result of being iterative, a lot of these workloads are really long running. So to train state-of-the-art image recognition models or like some of these speech models, it may take like many hours or a few days to run, even on a large cluster of like hundreds of machines. And as a result of being long running, they're very expensive in terms of both time and money for people who are deploying these applications. So this is a trend that we see on the workload side, and on the system side, the trend that we see that has been predominant over the last 4 or 5 years, which is, I guess, less surprising for this audience, is this trend towards cloud computing. Many of the consumer space applications have already been deployed on cloud computing, and more recently, we see even scientific applications being deployed on commodity cloud computing instances like EC2 or Google Cloud Engine, etc. So what happens when a new user who wants to execute some of these advanced analytics workloads goes to deploy some of this in the cloud? Before I get to that, there's also some recent survey on like Spark users that was done by TypeSafe, and it showed that more than 53% of the users actually deploy their production infrastructure on Amazon EC2, which is using Spark to run some of these workloads. So when some of these users go to EC2 and they want to launch their new job to run their machine learning job, what do they see? They see this really long list of like choices that they have in terms of the number of instances and the kind of instance that they can use for their job. So for those of you who've already seen this page in the Amazon website before, you'll realize that what I'm showing you here is actually not the complete set, and it actually extends for like 2 pages on either side of it. So on the one hand, the cloud computing providers have this view where they have a large number of instances with different types and different amounts of memory and CPU, et cetera. But on the other hand, the users have a different goal. Their goal is something like, I want to train my model within like 8 hours, or I want to spend like $200 and I want to train this model. So there's a sort of a disconnect between what the cloud computer systems are providing and what the users' goals are when they're trying to run these advanced analytics jobs. So this was the main motivation for this project, is to see if we can build a system that helps users deploy their advanced analytic applications better. So the first question that we asked ourselves was that, does this matter? Can you choose any of these instance types and will you get the same numbers? Like, does it even matter if I use like R3.extra large or 4 extra large and so on? So we ran a bunch of workloads across a number of instance types and tried to do some benchmarking to figure out what the performance properties were. So here we used a commonly used linear algebra kernel, a QR decomposition algorithm, and we ran it on machines of different sizes of the same kind. So here we used either 16 R3.large instances or 8 R3.extra large instances, and so on till 1 R3.8 extra large instance. So they're all normalized in terms of the amount of memory and CPU available, and we're running the same workload on all of them. The animation for this sort of like messed up how this looks, but what you can see in the graph behind this is that there's actually a huge difference in performance, even though we're paying the same price per hour across these instance types. And more surprisingly, what we found was that the smaller instance types, like the 8 R3.extra large or the 16 R3.large instances, actually finish the fastest. The axis here is actually showing the time it takes to run this computation. So this was initially a surprise to us, and so we did some more work in trying to figure out why this is the case. And some more detailed benchmarking of the instances themselves showed that you could actually get a lot more memory bandwidth, which is what these applications were sensitive for when you use a large number of smaller instances. So does this remain the same? Like, am I going to use the same R3.large instances for all kinds of workloads? It's not quite that way. So we ran another benchmark, which is a matrix multiply workload that's more communication intensive. And in this case, we found that actually one big machine actually saves you a lot of time on communication, and you can actually get much better performance on this one giant R3.8 extra large machine. So there is a factor here based on what your application is doing. Different kinds of instances might be more appropriate for it. So that's on the instance type that you want to choose. What about the number of instances that you should launch? So in this benchmark, what we did is we fixed the R3.4 extra large instance type, and we kept increasing the number of instances that we launch. So we went from like 2 to 4 to 8 and all the way to like 64 machines for the same workload. So initially, we see some benefits. So when you go from 2 to 4 to 8 machines, the running time halves for each of these things, and the price remains kind of constant. So you're actually getting like double the performance while you're paying like extra money for these instances. But after 8 machines, you see the performance sort of like flattens out. So when you go from 16 to 32 machines, the running time hardly changes, but you've now paid like double the amount of money for renting these 32 machines on your instance. And in some cases, we even see the performance goes worse. For example, like 64 machines performs worse than 32 machines. So you're not only paying more money, but you're getting worse performance than you could have. So the goal of this work is to say that you're given a job, and it's like input description. Can we help users figure out what is the optimal set and what is the number of instances that they should be launching for their particular job to complete? And to do this, the core insight that we have is that if we can develop a performance prediction model, that when you're given the job, it can predict the amount of time that it's going to take for different configurations that you have, then we can quite easily perform these like suggestions to the user on what kinds of instances they should choose. But building a performance model is actually quite tricky in this case. So for one thing, we don't know much about the job. It's like sort of a black box that has a lot of user-defined functions and doing a lot of complex things. But also on the other hand, to build the model itself, it could be expensive. As you saw, you have like 20 or 30 instance types, and in addition to that, the number of instances you can vary across a large number, from like 2 to 100, and so the number of possibilities that you have is like many thousands of possible cluster configurations for each given job. So the key insights in this work are, can we make it really cheap to build a performance prediction model while also still being accurate for a given user-defined job that we're going to run? Some of the main insights in our contribution here is that we try to build an end-to-end performance model from going from like the input to the complete model being built. And the key insights that we use is that most of these applications we find are very regular in behavior. And by regular, what I mean is that if you take a very small sample of the data and you run the application on it, you can try to infer its performance properties by looking at what it's doing on the small sample of data. So we exploit this fact, and we try to run the application on small samples of data and measure its performance and try to then predict what will happen when you run it on the larger sample of data. And finally, we also exploit the fact that these applications are iterative. So even if you run a few iterations of the application, you can try and figure out how its performance is going to look. And using that, we can again extrapolate to larger number of iterations. So let's see how we actually go about doing this and what is the science behind this performance model that we built. So one of the first things that we look at is like, how does the job look? So what is the structure of the job that we're going to be executing? Once again, the animation here it hasn't come out right. But at a high level, what we found was that there are a small number of patterns that keep getting repeated in these jobs that we see. So some common patterns that we see are these kind of like one-to-one patterns, which as you add more and more data to your thing, you get a one-to-one mapping between different tasks that are executed in the DAG. Some other common patterns we see are a kind of a tree aggregation pattern, where if we start with n partitions, then you have a log structured tree towards like aggregating towards one partition. This is, for example, found in a lot of the aggregation-oriented queries that people run. And lastly, we also see some linear patterns, where if you have n partitions of data, all of them are communicating to one machine. So this is, for example, like a broadcast variable would have like this linear pattern, or even some of the reduce operations that you might run in something like Spark will also have this kind of like linear pattern. So the key insight with seeing a small number of patterns is that we can actually build a very simple model if we're able to capture these patterns in our performance model. So what do I mean by that? So what I mean is that we can express the total time taken by the application as a sum of a number of terms, each of which capture one of the patterns that we saw in the previous slide. So I'll walk you through this a little bit more slowly. We have two variables here on this slide. The first one is input, which is the amount of input that we use, or the sample that we use to actually run this job. And the second variable we have is the number of machines that we use to actually run this job. Given these two variables, we can write out a performance model which looks something like this. The total time taken is the sum of a constant factor, which is the time spent in serial execution, shown here as A, plus a linear term, which is shown here as input by machines, that models the linear computation that goes on in parallel across all of the machines that you have. And then two terms which capture the communication patterns we saw previously. One to capture the tree communication pattern, which scales as log of the number of machines, and the other which scales linearly in terms of the number of machines. So the high-level intuition is that we can run this job on some samples of input data. We can collect some training data using the samples that we run, and then we can train a model to fit a model to learn values of A, B, C, and D for this equation. And once we know A, B, C, and D, given a new amount of data size or new number of machines, we can plug that in here and get an answer. So this is the high-level approach that we're going to do. So the next step that we did is, does the model that we saw in the previous slide actually match the real world? So we took a look at all of the MLlib applications that ship as a part of Spark, and we tried to classify what are the sort of patterns that occur in these applications. So here I show you the patterns that happen in GLM regression, k-means, naive Bayes, PCA, and so on. And we see that the few terms that we had in the previous slide are actually able to capture almost all of the patterns that we see in these applications. So this was very good to know for us because the model looks really simple, and we wanted to know if real-world data actually matches the model that we came up with, and we used the MLlib repository to validate our assumptions. So what next? Are we done? I mean, we have a model, we can train a model, and we can learn it, and it'll be all good. Well, there is still a problem, and one problem is that we need to collect some training data to build this model. And as opposed to other cases where you have a big data problem, we actually have a small data problem here, in the sense that we actually have no training data to start with, and collecting any training data is expensive, because you have to actually go to EC2, run a job, which takes some time and money that the user could have used to actually run their original job. So we had to figure out a way to cheaply collect enough training data so that we can build a good enough model and for it to not be too expensive. So the approach we take here is that we look to statistics, and we specifically look to a branch of statistics called experiment design. Now, the roots of experiment design come from a time where collecting data for doing real-world statistics was actually very expensive. Like, you can think of it in the 50s or 60s, agriculture required like a lot of statistical analyses, and it was actually expensive to collect data and took a lot of time to collect data in the real world. And so the high-level idea behind experiment design is that if you're going to build a model, which looks similar to the model that we had before, which is a linear model, you can use experiment design to figure out what are the important coefficients where you need to collect data for your model to be accurate. So to give you an intuition of how this works, the linear model that we had before is expressed here in this formula yi equals ai transpose plus wi. And the insight here is that the error in this model, or this model is given by the covariance matrix of the estimate that we have, and that estimate is actually independent of the actual model parameters, and it depends only on these coefficients AIs. And the intuition being that if you have a lower variance, then you have a better model. So given that insight that we get from looking at the model that we're building, we can actually formulate a small optimization problem where we want to minimize something related to the covariance matrix that we had. So in this case, the trace of the covariance matrix. And we want to find out which configurations actually help us minimize the trace of the covariance matrix subject to some constraint. So what is the constraint that we have here? The constraint is we want to minimize the cost. So you set a budget of like, I want to use this much time in order to do my training. And then you try to find out which are the configurations that I should choose so that I can actually finish training within that budget and yet still minimize the amount of the variance that my model has. So having set this up in this way, we can actually just use an off-the-shelf solver like CVX and get what are the optimal configurations for the specific problem that you have. So just to take a step back, the workflow that happens here is that we give this procedure a range of machines we want to explore, like say between 1 and 8 machines, or between 1 and 8% of the input data. And then we feed in this range of data points that we can choose from to the CVX solver, and it returns back these red dots which show like, oh, you should collect training data at 4 machines and 1% input, and at 1 machine and 2% input, and at 2 machines and 4% input. So this helps us formulate the jobs that we'll actually run for training. So let's just summarize the whole procedure here that we use for performance prediction. So we have a job that the user wants to run and some input data that the job is going to use. And we feed both characteristics of both of them to the experiment design model that I showed before. So that tells us how to collect training data, and then we run some small training jobs on an EC2 cluster. We use a few iterations of the job to do the training, and based on the training data that then we collect, and we build a linear model based on that. So putting it all together, how well does this work in practice? So the same Timid pipeline that I showed you earlier on, right at the beginning, the Keystone ML pipeline that is used for speech recognition, we collected training data up to 16 machines, and then we tried to predict its performance on 45 and 64 machines, respectively. So what we saw was that the prediction error is actually pretty good, and it's within like 15 to 20% of the actual running time when you run it on 45 or 64 machines. More interestingly, what we found was that the training was pretty cheap. So it took only like within 5% of the overall runtime for us to actually train this model. And so we can actually use this prediction as a low overhead prediction for the jobs that we're going to run. We also tested it on all of the MLlib benchmarks that I had shown you before. And we found almost similar behavior where the error was within 15 to 20% of the actual runtime on 45 and 64 machines. And finally, we want to work through an example where we can show how the performance prediction is able to catch some non-intuitive behavior that you wouldn't probably expect. So that Timid pipeline, when we scale it across a large number of machines, we see the scaling behavior where it sort of like flattens out across over time. And the model that was learned using up to 16 machines is shown in these red dotted lines here. And it sort of captures how and where the performance plateau happens. So in this case, we can see that, so the zoomed in version of the left-hand side is shown on the right-hand side. And we see that it's actually fastest when you use like 40 machines or so, instead of using 120 machines to run the same workload. And at 40 machines, it takes around 57 seconds. And after that, it actually increases to like 60 or 65 seconds. And this is for one iteration of the job that I showed you before. So hence, the overall takeaway message is that using the model that we built, we're actually able to figure out what is the optimal number of machines that we should launch for a given workload. So what's next here? So this is some very recent research we've been doing, and what we're trying to do is put together an open source tool that you can play around with, and that you can give it your own jobs and see what are the performance predictions that it makes. We're also trying to run many more workloads on this. So after this, you're going to be hearing a talk about Adam, which is this genomics framework, and we've also used that to see how well can we predict the performance of those jobs. And also, we're planning to run it on large traces of other like machine learning queries that we have. And finally, there's also some very interesting research that we're doing on trying to predict when the model will not work. Like, let's say you have a job where the model does not fit your job. Can we actually tell you that the model will not fit your job and sort of like prevent giving you wrong answers? So I'd like to conclude by saying that with this shift in trend towards advanced analytics applications, there are a lot of challenges in deploying them to like commodity cloud computing infrastructure that we have. As a part of this work, we specifically looked at building performance models so that we can do performance predictions with low overhead for these workloads. And one of the artifacts that we're going to build as a result of this is an open source tool that you can use with an Amazon EC2 cluster. We're always interested in like listening about more real-world workloads that you might have, or any other traces that we could use for driving research and like evaluating how well our research works. So feel free to shoot me an email if you have anything like that. And with that, I'll conclude and take any questions. Thank you. Going once, going twice, gone.
Thanks, Shivram. I think you convinced everyone. Our next speaker is going to be Frank, and he's going to talk about Adam. And he will talk about how to make genomics faster.
You're do PDF as well? Is that correct? You do a PDF? Okay. Lowest common denominator for compatibility. It's true. Is it just mic'd over here? Yes.
All right. So thank you all very much for coming out. So I'm Frank Notaft. I'm a third-year PhD student in the AMP Lab, and I work at the intersection of computer science and genomics. So I'll be talking to you today about Adam. So Adam's a system that we've been building for doing large-scale parallel genomic analysis. So you know, everybody nowadays is talking about genomics and precision medicine, and you know, I think many of us know at some sort of abstract level what your genome is. And the simple way to think about it is that genomics is, your genome is the source code for life. It's about 3.2 billion letters long, and it's split across 46 files, 23 that you get from your mother, 23 that you get from your father. So these files in biology we call chromosomes, but for here we can abstract it away as just a bunch of long character sequences. One of the things that's very interesting about genomics, what makes it very different from programs, is that every single copy of this program for life is actually largely the same. Whether it's mine, yours, we're all about 99.9% the same. On average, we differ at one of every 1,000 sites. Additionally, most of the source code is comments. The actual part of the genome that codes for proteins is less than 0.5% of this whole 3.2 billion letters. You know, the big questions that we're looking at, though, when we have your genome, we go ahead, we analyze it, because we're looking for, you know, these 1 in 1,000 position differences to see how they associate with the different traits and the diseases that we're affected with. And you know, we're not just looking for differences that happen in the part of the genome that code for a protein. This area, this 99% of the genome that doesn't actually code for proteins, you know, it's not just comments. You know, we know that it does have an effect on traits, even though it's not a direct effect. So the way that this works, I assume that most of you aren't familiar with sequencing machines, is it's actually a simple thing to reason about. It's a Poisson sampling process. So when we go ahead, we sequence your genome, what we do is we divide this 3.2 billion letter source code into a bunch of short fragments. We duplicate them a bunch of times, and then we essentially pick 100 base long fragments out of that. So, you know, we're going to go ahead and reconstruct this 3.2 billion letter long book out of 100 base long sequences. And, you know, if we want to get 30 copies at each position in the genome, we can do that for about $1,000. So that was a very big accomplishment. You know, it's actually, since the Human Genome Project occurred in 2001, the cost of sequencing a human genome has dropped by over 10,000 times. And, you know, so that's the progress that we've seen in 15 years. And, you know, we expect to see costs dropping, not necessarily as fast as they've been in the past 15 years. We're not going to see another 10,000x, but we'll see, you know, we'll see sequencing costs continue to improve. And, you know, the big implication here is that while in 2001, when we had this Human Genome Project come up, we looked at 20 individuals' genomes, and this cost about $1 billion to do. Now that we have this very high quality understanding of what the human genome is, we can use a simpler process. So what the Human Genome Project did was it generated this consensus for what every single one of our genomes look like on average. You know, as we said earlier, 999 out of 1,000 places, we match more or less. From this, what we do is we'll take your individual genome sequence, we'll go ahead, compare it to, you know, what we call the genome reference, and we'll compute a diff. So this leaves us with two big problems. And the first is, how do we go ahead and compute the diff? And then the second is, how do we go ahead and make sense of the differences? So while this is much cheaper from a cost perspective, it's still fairly expensive to do. What we're doing is we're actually going ahead and we're going to take every single one of these sequences. We're going to align it. You know, you can think of the text on the top, you know, the reference copy. We're going to align every single fragment to this reference copy. And then we're going to run a statistical algorithm that goes ahead and finds a consensus sequence at every single place. So, you know, in this slide, I don't have any errors in the text. You know, when you look up here, it's all good words. I didn't misspell worst when I copied it. When we look at a real human genome, though, you know, in addition to the differences that we expect to see, this 1 in every 1,000 positions, we actually have an error rate of 2%. So we have, you know, errors in our sequence that are more common than the variance that we expect to see. So, you know, that's kind of what we're trying to go ahead and factor out. This whole process is actually fairly expensive. So, you know, what we went ahead and did in Atom was we came up with a greenfield approach to this problem. So this right here is a picture of the reference genome. You know, it's the best practices genome sequencing pipeline. So this is called the Genome Analysis Toolkit. It comes out of you know, the Broad Institute of Harvard at MIT, and it's one of the most widely used tools in genomics. So when you're going through this process, you know, we have this first stage up here that, you know, we're going ahead, we're doing the sequencing, you know, this Poisson subsampling process, $1,000 gets us our data. The next steps from, you know, right here where we hit this map to reference, this is the string matching problem, all the way to the end where we actually get this diff, takes about 150 hours to run and can be, you know, about $500 worth of compute. So it's a very expensive process, and people have really optimized this for this case where you have a single machine that's very big that you're going to store all your data on, you're going to process it on a single machine. You're not going to go very big, you're not going to go parallel. Unfortunately, this has led to several very big problems in the genomics community. You know, since people are building in this environment, they're traditionally building for things that look like HPC HPC-style compute clusters. This process is actually I/O bound. You know, when we talked about generating the 30x replica of the human genome, that consumes about 100 gigabytes of data. So, you know, we're going to go ahead, we're going to read 100 gigabytes of data to do this compute process. And right now, every single time we run a stage, we write it to disk. So, you know, we're violating a lot of these assumptions that we preach for in Spark. And if we're building in an HPC environment, you know, if we did want to go parallel, we're going to wind up being constrained by the storage bandwidth that we get going to a shared file system. A lot of these pipelines also make interesting assumptions about how data is laid out. There are a lot of optimizations, both in the file formats that people use and the way that we traverse over our data that are really specific to this one application. You know, they do very interesting optimizations by pushing down sort order invariance into their data, and this winds up making it very hard to go ahead and combine tools. So while, you know, I could run the GATK, let's say I wanted to sub out one of these stages. You know, someone comes up with a new method, I have to go ahead and figure out, you know, is the sort order they're using in their method compatible with the sort order I'm using in my method? It makes it very hard to combine tools. It makes it very hard to run tools in parallel. So we went ahead and we took a step back, and you know, we did what, you know, many people who are educated in simple database design did, and we decided to factor everything out and just come up with a schema that defined the genomic data that we were working on. This is actually the first thing that we did in Atom, and it's been very interesting because some parts of genomics have very well-defined schemas, some parts do not. So you know, I'll talk a little bit more about that later. From that, the schema provided a very nice narrow waist that we could work against. So if I'm writing some genomic algorithm, I'm going to have an RDD, and that RDD is going to be full of, you know, of just little objects that have this schema, right? You know, we actually use Avro for our serialization, but you know, you can load up our data in a data frame, doesn't matter. On top of this, we've gone ahead and we've accelerated a lot of the common access patterns with higher level primitives. So one of the things that's very common in genomics is you do this very special type of a join. So, you know, the thing that's interesting about your genome is that, you know, as I said earlier, you have 23 chromosomes. You get 2 copies of each, you know, one from your mother, one from your father. And, you know, a lot of things in genomics are described by where they are on a specific chromosome. So, you know, you might be interested in a gene that is on chromosome 17, position 235,000, right? So very frequently, we're going ahead and we're taking, you know, genomics data set 1. Maybe it's a set of areas where I am different from the average human. And, you know, genomics data set 2, it might be a description of all of the genes that are in the human genome. And we're doing these joins on them. We're doing them fast. You know, we want to do them fast, but it's not necessarily something we can do fast natively. You know, the naive implementation in Spark would actually take about 90 hours to run, you know, on a fairly reasonably sized cluster. But the optimizations that we've made takes that 90-hour runtime, brings it down to 1 hour. And there are other nice things about this. You know, this is a very common pattern that people use in genomics, but as I said earlier, the way they accelerate it is by pushing down these sort order invariants into their file formats and writing against these very low-level abstractions. So when we're going ahead and building Atom, we verified, you know, performance by rebuilding some of these canonical algorithms that people are using to run, take 150 hours to run. When we rebuilt the algorithms, you know, we found that not only were we able to come up with good ways to scale them in parallel, but we actually identified several bugs in the algorithms that came because they were writing at this low level against this, you know, sorted iterator across the genome. By writing at a higher level, it made it, you know, 1, much easier to write the code, and 2, eliminated bugs in about 4 or 5 of the stages that we were interested in. Additionally, we've gone ahead and we've, you know, after designing our schemas, we decided to pick an appropriate storage format for the data. As I've discussed, you know, a lot of the storage formats in genomics are optimized for, you know, the traditional use case where you have, you know, 1 read, you have 2 reads, you essentially have a row-oriented row-oriented storage. However, this isn't necessarily a great fit for science. We're frequently going ahead and slicing and dicing our data set. it's actually very common that the first analysis that you run is only going to look at about 6 fields out of the 33 field schema that I was showing a couple slides back. The 6 fields that we're looking at here are less than 2% of the data stored on disk. By going to a columnar storage format that allows us to, go ahead and project fields out, as we need them, we were able to get just a 10x performance increase right off the bat, and we were able to improve how our algorithm actually scaled out. Additionally, we're frequently running selective predicates. So, while I might be interested in analyzing the whole genome, someone else might come along and say, oh, I know I'm only interested in chromosome 1. If they're only interested in chromosome 1, they can go ahead and throw away more than 90% of the data just by applying that one filter function. And that's something we can very easily optimize by using columnar storage. One of the things that's been very interesting as we've gone through the Atom project is that many people have criticized our choice of going ahead and rewriting our schemas and using a different columnar storage format on disk instead of these legacy file formats. Actually, we've several times had people tweet this exact figure at us. And the thing that's actually really interesting, and this is a really subtle point about the stack design that we use, is that by putting the schema as the narrow waist, it's easy for us to go ahead and write our algorithms against our optimized storage format. Well, it's not optimized, it's just a commodity columnar store. We use Parquet. But it's very easy for us to go ahead and run our algorithms on any of these legacy data formats. So in genomics, there are about 5 different key types of data. Some of them have 1 or 2 well-accepted formats, but in other of these sets of data, you'll have more than 5 or 6 different formats that describe the same basic model. So by having this, having the schema in the middle here and being able to switch out how our data is materialized on disk, we actually are able to work, we essentially provide anybody who's writing an algorithm that processes genomics data in Atom with, they can be agnostic as to how their data is actually stored on disk. They can save it into our legacy, into our columnar format. They can save it to any of the legacy formats. They can read from any of the legacy formats. So it gives them a lot of flexibility. They don't have to worry about whether their algorithm interoperates with something by reading the same bytes off of disk. So all of this architectural stuff is nice, and it provides great benefits if you're going ahead and writing these genomic algorithms, and you don't want to worry about writing at a very low level or worry about what your exact bytes look like on disk. But nobody really cares if it's not fast, right? So again, our big mission at the start was to take this 150-hour pipeline and to get it to be not 150 hours. So we focused on, on these stages that are here in the middle because they're very expensive stages. In the 150 hours, you actually spend about 100 to 120 hours just in these 3 stages. So, this is kind of a performance result that we had from a paper that we presented at SIGMOD. We achieve linear scalability on a single genome out to 128 nodes. So here we're evaluating ourselves on a 250 gigabyte data file. So this is one of the largest human genomes and it's a human genome that people use to evaluate many tools on. So it's a kind of a standard data set that's used. On a single node, what we did was we compared our performance on a single big node to the state-of-the-art tools on the single node. We ran several of these different stages. We picked the fastest performance of any other tool out there, and we compared against our performance. On a single node, we would be up to 3x faster, and then we would scale out linearly to 128 nodes. And on 128 nodes, keep in mind this is about 200 megabytes of data per machine. So we're operating with a very small amount of data per machine, and we're still getting a very good parallel speed out. Since we've gone ahead and run these experiments, we've actually made a lot of single-threaded performance improvements inside of Atom that have given us between a 1.5 and 2.5x improvement uniformly across our code. So that would mean, we're no longer 3x faster on a single node, but we're about 6 to 9x faster. One of the great things about working on this project is that we've had many collaborators that are out there. So Atom is a project that has about 46 collaborators in the open source field. Many people here at Berkeley, but a few folks at other hospitals such as Mount Sinai in New York, and people in industry at Cloudera and Microsoft Research. If you're interested in genomics, or you'd like to talk more about how you can scale genomic algorithms out faster, please feel free to find me later, and I would love to talk and let you know about how you could contribute or use our code. Any questions? Thank you very much.
So with that, we have come to the end of today's sessions, and from 6 to 8:30, we have some small reception down the hall in the Great Hall of the International House. And other than that, we're going to see you tomorrow morning again. And for those with Windows, I'm sorry, and I would suggest, like, if you can, please try to download sort of VM image tonight so that you can carry on with tomorrow's exercises. Thank you.